Hello, everyone.
Hey.
Okay, so Ibi, can I start the presentation right now?
Yes, you can go ahead. One small comment, please, for those that are in the meeting, if you're not speaking, please
everyone.
mute yourself.
Okay. So, good evening, good morning, good afternoon, depending on the time zone. My name is Anton Kolonin, and I'm going to give a tutorial on what I call building online environments for social artificial intelligence agents with AI agents. And the talk that I'm going to have now is not that much about the AGI itself. It will be more about building the environment where we can build very specific kind of AGI. I would call it narrow AGI, intended for social intelligence and specifically online social intelligence. That means we are trying to create a environment and ecosystem and the platform where one can build AGI agents that would be capable to perform intelligently within the online media and social media, serving either group users like companies or communities or individual users. So there are two reasons why we are selecting this direction that I'm going to talk about today. The first reason is that we are assuming that instead of building completely general artificial intelligence at once, we will try to first build what Ben Goertzel called narrow artificial general intelligence last year on the AGI 2019 conference. So the idea is that before building completely general AI, we are trying to create specific segments of narrow domains that are on one hand narrow, so we have some limited area, limited generalization possibilities, but still there are a lot of ways where the ability to generalize, to perform experiential learning, to perform reinforcement learning, to adapt to the environment still can be implemented. And the other reason why we are selecting this direction is that we are considering that intelligence on itself is a product or byproduct or a product of co-evolution with the social structures and language and social communication media. By social communication media, I mean just the ways people use it to interact with each other and animals use it to interact with each other millions years ago. So me, like many other people, assume that the nature of human intelligence is ability to communicate and act within the society. And so then building a model of artificial intelligence which has some properties or some structures underlying the social nature of the intelligence seems like a reasonable and useful challenge that we are trying to solve along the way. So in this talk, I am going to give just overall overview of the goals, use cases, and capabilities of what we call AI agents platform. And then if there are questions and if time permits, I would be able to either go to some online demonstration on what we have in the agents platform right now, or just go into the code and see how all that stuff is organized at the level of the code that we provide as open source under MIT license. So from business perspective, we have two ideas of how the agents platform can be used. First, It can be used as a group agent of general intelligence, serving either companies or communities. And so it can, it makes it possible for teams and groups of people to join heterogeneous social and online media sources and blockchains, payment systems, and then couple them with artificial intelligence. So participants of these groups are able to find and track changes in the field of information, which is actually exceeding the capabilities of people. If you experience it, and if you are consuming information online, so the people can actually utilize the force of information in efficient way. So right now on this slide, you can see all the platforms that we are supporting right now, and we are keeping to increase the support, level of support and depth of support for each of the platform along the way, and we are gradually adding more and more sources of information. So we support blockchains, social networks, RSS, web pages, forums like Discourse, and messengers like Slack, Telegram, and Facebook Messenger, Slack, and Telegram, and we make all information integrated, analyze it, and I will show what we do about this information. And another case which we support is providing a personal agent of artificial intelligence or agent of personal artificial intelligence for individual users. So the agents may serve as a magic glass or a crystal ball in the world of social and online networks for people. So it can recognize people's preferences, help them to find what they need, help managing social connections, and make these connections to be safe and joyful and pleasant. And also for this purpose, we support all the same sources and social and online media that people can use in everyday life online. So far, here's our roadmap. So from the bottom to the top is where are we going. So we started with trying to create personal agent for individual interaction with the information online. Then we moved to creation to create a capability for groups of people, so agent can be shared by groups of people, and or multiple personal agents can be unified within the same workspace. So agents serving different people can share information with each other, serving the whole community at once, implementing the principles of collective intelligence that I will show later. And now we are moving to the next goals. So one goal is to making the personal agent more personal, to actually try to get deeper into the personal profile of a person, so it can be actually helpful making advices for people. The people you can use these advices to be more efficient in personal communications with other people, and be safe and be efficient. And another direction where we're going, so we are trying to create an open source platform for engineering smart agents on the AI agents platform that can be applied for different domains in different business applications. And of course, we are open to partnerships, and since we are using providing open source. And now let's go back to the subject of our conference. So but before doing that, let's talk about the definition of the general intelligence, no matter whether that's artificial or essential or natural. According to multiple definitions of the general intelligence made by Ben Goertzel and Pei-Won and many others, here is the definition that is close to my own understanding. So we are talking about that we need to be able to reach complex goals in complex environments using limited resources. And the extension of this definition is that the complex environments may be different. So if we are capable to operate in one complex environment, then we can move to another complex environment and adapt to it. And also when we have multiple goals and complex environments and limited resources, we need to be able to minimize the risks. So we need to be able to see if we need to find different goals and are using different roads leading to these goals, and then we can avoid certain dangers, and some dangers may be more dangerous, some may be less dangerous, and we should be able to deal with all that complexity and multiple goals and multiple features of the environments. And then the idea of the narrow artificial intelligence suggested by Ben last year, as I understand this idea, is that we can have different levels of complexity on the goals side, on the environment side, as well as limitation of the resources may be different. Like if we have infinitely complex goals and infinitely complex environments and infinitely limited sources, we are actually having infinitely general intelligence. If we have not that complex goals, not that complex environments, and not really limited resources, then we have really really narrow intelligence. And somewhere in between, we have moderately complex goal, moderately complex environment, and resources limited to some extent. And then we have what we call narrow general intelligence. That's neither completely general nor narrow, but somewhere in between. And we can actually constrain specific source of narrow intelligence. Like one sort of narrow intelligence is biological intelligence. All right, so let's consider rats or mice. So rats and mice have intelligence general enough so they can operate in a forest. They can, but they can also adapt to the maze. So they can survive in a maze just after a certain period of adaptation. The very recent experiments show that the intelligence of these animals is general enough so they actually can operate the vehicles. So if you put a rat or a mice on an electric car, as experiments show, it can actually adapt to it. It can actually operate the electric car in order to complete the goals that they are experiencing without of having these devices. But still, you won't ever be able to read a mouse or rat to browse the web. So it would never be able to browse the Google engine or to go follow the links on the websites in order to find the food or find another another animal to breed and to give offsprings. And here we have another kind of narrow intelligence. So that's narrow online intelligence. And that's actually is the nature of the project. So we are trying to create the narrow general intelligence for operation with the online information. So the agent could be able to do with web search, with web browsing, with social network information handling, with interacting with another participants of the online environments using the tools of the online communication, like posts, comments, messages in the chat systems, like messengers, likes, votes, etc. And then we are finding that we need actually solve lots of complex problems, starting with navigation problem, like is shown on this slide. So agents should be able to navigate within the multiple links or multiple search results returned by the search engine in order to minimize the time wasted reading irrelevant posts, in order to avoid particular pages that may be not loading fast or maybe just not available. Also eliminating fake news or the information that might be just irrelevant in the end or not reliable at all. So here is the problem one that we solve actually. Make the time-critical news monitoring more precise, reliable, safe, and cheap. So the use case is like, I am a user and I'm interested about particular area like because of my business or scientific interests, and I am creating the agent, and I am training this agent to do the information search for myself. And besides doing the search for myself, it also can do the search and monitoring of the information when I sleep or when I'm busy with something else. And whenever agent finds something new and relevant to my interests, it returns this information to me, so I'm saving my time. And during this case, the user should be able to configure a custom combination of online sources, so it can further narrow the area of search and monitoring for the agent. And also this configuration may be extended by the agent itself. So once the agent is smart enough, it can also add some more information to this configuration. Then the user should be able to specify precise alert and text patterns. So the user should be, when user is posing the goals to the agent, user should be able to specify the criteria for reaching the goals, for actually completing the tasks that agent is posing. By the way, tomorrow we will be given a talk with Evgeny Vityaev on the task-driven approach to the artificial general intelligence, and that would be much more mathematically and theoretically rich from the AGI perspective, rather than now. Now we're talking mostly about practical and application-specific details. But here we go. So actually specifying patterns that agent should be capable to match on the online in the field of the online information is exactly about defining the task in terms of criteria that is satisfies the achievement of the goal by the agent. And then we are using artificial general intelligence AGI to let agent learn how to find the critical information using the pages, links, and search engines. Finally, we let agent provide timely alerts when news items are found and extracted from online texts. And finally, when there is a lot of timely alerts with news items extracted from online texts, it may be still too much information for for a user to comprehend. So the agents can learn from the user using experiential learning, so they can figure out which kinds of information items may be more interesting for user than others, and so then amount of information can be restricted down to the top few items. And also agents can communicate, applying collective intelligence, so the relevance of the news items found online is assessed based on the collaborative filtering of collective intelligence. So briefly, how it works. When a user gets an agent installed or registered with online hosting of an agent, it can let agent look up user's profile on one or another social network or one of the messengers. And so the agent can look into the posts and messages and comments and likes of a user, and agent can build a brief initial profile of the user. And this profile includes the patterns that user might be interested to search for, as well as websites where the search and monitoring of information can start with. When along the timeline, when the agent is operating, it starts searching and monitoring for information accordingly to the text patterns and accordingly to the web sources or websites or URLs created for the user profile. And along the way, user is also able to contribute to this, to make the agent smarter. So on one hand, user can explicitly change the profile. So the profile is represented to the user in terms of what is called interpretable representation or explainable representation, instead of besides building black box kind of a neural model of a user, the agent actually ends up with creating specific text patterns that are readable. So the patterns I will go in details of the pattern architecture and representation later, but it's anyhow it ends up with specific complete words or phrases that can, or variables that can be comprehended and edited by user, and user can also explicitly tell agent other keywords and phrases and variables, or remove what user thinks that agent is not right. So agent may be just completing some, creating some junk patterns that user might not like. And so the same is true to URLs. So if agent created some URLs that actually are not relevant to user, then user can remove them, and user can add them, and then it can actually explicitly operate the agent performance. Another way how user can help its own agent to help the user, it can implicitly provide the feedback. So the feedback is provided in terms of just providing likes or check marks or votes in respect to specific news items. Like if I like something, I put my check mark or like that news item. If I dislike it, I remove. And agent incorporates this feedback and it does the inferences in order to create better patterns, in order to find more suitable sources where to look up for information, and it also provides the account for the relevance of the news items like shown on the next slide. So here, when you see the news feed created by the agent based on the sources and patterns, each of the news items is indicated with the bar, like blue bar and green bar here. So the blue bar indicates the extent to which the news item is relevant from the agent point of view to the items that user liked in the past. So that's what we call personal relevance. So if the blue bar is high, then most likely that's relevant to what user liked in the past. But there is another bar. On the current screenshot, it's green, but in current user interface on the aiagents.com website, it's rendered as yellow, is what we call social relevance. And that's where collective intelligence comes into play. So the size of the green bar for social relevance is computed based on the amount of probability that these posts will be liked by users connected to given user. So the user may have friends in his or her network, and the friends may be also using the agents, and they may be also providing some feedback to these agents. So what the agent learns from the other users in my environment, it is reflected here as a green bar or yellow bar in the current user interface. So here is the second problem that we are trying to solve, and that problem is much more about social intelligence rather than just providing collective or social relevance assessment of the news items. We are trying to let this agent help people to make personal online communications more useful, safe, and efficient. So we are trying to help people with our agent to find the right leaders on social media while interacting online. And there are too much people around, and there is no way to actually know each of the people that we are encountering on the social networks. Then we are trying to improve these relationships with friends and colleagues, getting rid of annoying connections, and trying to make reliable and useful and pleasant connections more solid. And finally, helping to find target audiences for the purposes of personal and business promotions, improving loyalty for businesses or for personal need. So while the first case about the news information is actually, I would say it's 99% working, the social intelligence part is still in active development. So what will be shown on the next slide is a kind of imaginary flow for mobile application use, which is not operable right now, but like 75% of its of this is actually available online. So if you use our online version or web version, you can do actually almost the same, but just using a little bit different representation. So basically, the idea is that when you set up your agent, as in the following case, you with information analysis and monitoring, you also let agent access your online communication channels like social network, messenger, and so forth. And then agent can learn from your information exchanges with other people and with these systems, but it learns not what you like or what you post or what you comment on, but it learns about your social connections. It learns what you are saying to specific people, what particular people are saying to you, what you like in the posts of other people's, what other people like in your own post, etc. And the idea is that you can specify different communication channels that you can let agent analyze, like email, messages, web navigation, actions, different social networks. And then based on this communication, agent can extract your information and build your interaction graphs. And on these interactions graph, it can understand not only the semantics of this information, like what you are talking about with different people, but also sentiment of these interactions. Like some interactions may be positive, some interactions may be negative, like on this screen at the bottom, you see there are two red arrows and green and more green arrows, and the thickness of arrows represent amount of information. Like the most communications on this graph are done by John Doe to Mary Jeans and John Grow. And there are many other green arrows that are about positive sentiment communications, but there are two arrows. And the red arrows are from Jerry Stranger to myself, John Doe, and that's negative communication. So maybe Jerry Stranger is saying something or writing something really distracting or unpleasant to me. But there is another red arrow where myself is saying something not that good to Joy McLean. And we'll get back to this case a little bit later. So here is again how we set up the agent. And here what we can do with the data learned along the way. So on the left, we can see the representation of different people, how we interact with different people. So directions can go from people to us, from us to people, and direction. And so we can see green or red bars from left to right and from right to left. And then we can also see the yellow bars. And the yellow bars, as well as the saturation of the yellow color on the graph in the middle, corresponds to what we call reputation. So the one important feature of the social intelligence that is that people are capable of, and we think that artificial social intelligence agents should be capable of, is computation of the social rating or social reputation or social capital or karma, whatever you call it. And the agents should be able to properly do assessment of this reputation. So yellow bars and yellow color saturation represents amount of positive or reputation or karma within the social network or a personal social network environment of the given person. And we can see that Bill Ashley is the most, and Mary Jeans are the most reputable people in given environment, while Anthony McGregor and Jerry Stranger are the least reputable guys in this environment. It just happens so for given case. And what we also see that there are these red arrows, And we should be able, and actually we can do pretty much of what is rendered on the slide right now, but there are few things that we can do that now, but we are going to be able to do that soon. So you can see that agents should be able to monitor these interactions and provide some alerts. Like, for example, the agent may discern that, okay, it says on the left and the bottom, so that your last email may be hurting your friend Joey McLean. And also you have angry runs in Facebook comments from Jerry Stranger. So the agent should be able to actually give you some advices in order to, you may be able to avoid Jerry Stranger, and you may send some excuses to Joey McLean if you really want to keep your relationship with her. And then over the time, the dynamics of the interactions or development of the social environment may be tracked. So on the right, you see the historical diagram where you can see amount of positive sentiment that the agent is receiving, and that's in green, and amount of negative sentiment that agent or person represented by this agent is receiving, and that's in red. And then you see the karma of a person. So the karma is represented by the yellow bars. So you can see how the karma development changes from the sentiment of the incoming and outgoing messages. And so the agent may actually predict and find the causal relationships between specific actions and specific messages, and change in the karma or reputation level of the user, and make recommendations like you should send excuses to Joey McLean, you should avoid Jerry Stranger, and finally tell that, okay, so during the last week you have your karma improved because you just kept your relationship with Joey McLean. And further, just to see how we are dealing with all that stuff, let me go deeper into the design, and I would say conceptual design of the whole data representation model. That is relying on what we call social evidence, or social evidence-based cognitive model, which is which has been presented on the BICA conferences in 2015, 2016, and 2017. So the idea of the social evidence is actually going along the idea that the nature of the human intelligence is social. So that word separate talk, but the idea is that we can think because we can talk, and we can talk because we have someone to talk. And since we have someone to talk, we need to think about those people. So in order to, when we are doing the communication and verbal and conscious activity, trying to describe abstract models of the world, we are always operating within a context of the specific people. And so if we are trying to build an agent which is capable to interact or act within the social environment, then agent should be able to have at least a social kind of representation in respect to a single person, the user of the agent. So if there is artificial intelligence agent that has to be created, then there should be at least society of at least two users, the agent and the master. And besides having its own personal image, the image of self of the agent, the agent should be able to have the image of its master. And the interaction between the agent and the master of the agent should be conducted, performed within the context of this, of the interaction of these two images. But if the agent is serving the user within the social environment, then the agent should be able to represent the images of the other users who are owners of the other agents within this environment, and who are friends or colleagues or co-workers or family members of the user who is the master of the given user. So in order to represent all this, we have came up to the model which is presented on the current slide. And what we do here, we actually, and of course, we assume that the knowledge is represented with graph, whether that's a plain graph or hypergraph or metagraph, like in OpenCog, that's quite another story. So different graph representations are out of the scope of this discussion, but let's assume there is some sort of graph. And if there is some sort of graph, we can break it into 4 different segments. And each of the 4 segments would have kind of a little bit different operation properties, or different meaning, or different computational logic, or different sorts of implications and manipulations done with this subgraph in respect to other 3 graphs within this model. At the very top, we see what we call foundation graph, or we can call it upper ontology, or we can call it belief system. So that's something which doesn't require an inference. Like Earth has form of sphere. The sky is blue. People are intelligent, and etc. So these are terms that we don't have inference applied to in our everyday life. And so certain things may be kind of hard-coded in the foundation graph for the agent as well. On the opposite side, at the very bottom, there is evidence graph. So the evidence graph is just a flow of afferent stimuli that is coming to the channels of the agent's perception. So whenever agent is seeing online pages that agent is reading, text messages that agent is receiving, posts, comments, likes, votes that agent is finding online, so everything is coming as evidence. And that evidence may be positive, negative, it may be true, fake, etc. It's just evidence. But in order to do assessment of this evidence, the agent can be assuming that every piece of evidence has some connection to some social reference. And the social reference may be either the source of the information, like post by someone, comment by someone, message from someone, or it may be assessment of particular property of information from some social reference, like your mother thinks that doing this is bad, or your father thinks that what the other guy said is false, or your sister thinks that what this guy is saying is true. So we can have positive or negative assessments, we can have truth or false assessments, but all these assessments may be given by specific people, and these people or sources of information are stored in the social graph, which is on the left of this picture. So whenever you have something in the evidence graph, it is based on some entities that are known in foundation graph, it is assessed for relevance or sentiment by someone in the social graph. And then you can do the inference for the items that are getting in the imagination graph. So if you need to make decision about anything which is not present in the foundation graph, which is not part of your belief system, which you just have to make decision about, then you just ground it on your foundation graph, you take all evidence from the evidence graph, and you assess the reliability or sentiment of it with the references you have in social graph, and you have final assessment of the probability, trustability, reliability, positiveness, negativeness, and so forth, and then you make this decision based on the current image of the world that is present in imagination graph. And that's what our agent to do in its own cortex, artificial cortex, and that's what we're actually doing. Another perspective of the same model can be represented not as with circles, it can be represented with different layers of a cube, and you can slice this cube in 3 directions. On the left, you can see how we slide this cube from the bottom to the top. So on the low level, there is evidence. On the top, there is a foundation. And we can go from one layer to another, like if we take evidence, we do inference and compute items in our imagination graph to build our current view model. And then if some items are asserted to be true in our imagination graph in our current world model, eventually we can hardwire them and place them into a foundation graph. So that means if something is true due to our inference based on the evidence, and it's true every day, then there is no point to make any inference about this. We can just hardwire this into foundation graph and keep it residing there. And that's and we save our computational resources or our organism resources. So that's one part of the design. Another part of the design is coming from the other inference, and that's social aspect of the inference, and that's on the right cubes. It goes from left to right. So there is a part of the graph and knowledge is social, and other is non-social. And when we do the inference, we use all social reference to compute non-social knowledge, which is actually becomes our point of view. So once we decided something, it's part of our worldview, and we may eventually forget that that was inspired by some social motifs or social weighting or social-based inference. And finally, there is third direction in this cube. So it's from it's on the very right. So it's from the it's about short-term memory and long-term memory. So on the front, there is a short-term memory. On the on the back, there is a long-term memory. And if we are trying to focus on something, then we can get something from the long-term memory. That's hard drive or persistent storage on our case, and we bring it to the short-term memory, which is cached in the random access memory in our case, and we are focusing on the information in this way. But if we don't need something in our current attention focus, we push it out from the short-term memory back to the long-term memory, and eventually we can forget it. So we garbage collect the items that we don't use, and we keep the space on the hard drive for persistent storage. Now let's move on to the overall architecture. So here is the chart describing how it was designed before a line of a code has been written. So, and by the way, all parts are in place right now. We are just getting much more parts now. So by design, what we have got at the very beginning, on the left, there is communicator module or subsystem, and communicator is just a way to get information from any source and push information back to any sources. So emailer takes care about the emails, SMPP about text messages, CMD liner is about interacting on the command line console, TCP peer and the HTTP peer are about interacting on the TCP/IP or SSH or HTTP protocol, etc. And then the interaction from communication is coming to the conversationer, which is in the middle. And the conversationer is connecting with communicator using the text processing modules, which are reader, and AL stands for AI-agents language. So the AI-agents language is what is called controlled language or strictly constrained dialect of English, oversimplified dialect of English, and it's oversimplified almost to the turtle syntax. So if someone knows that turtle language is a language used in semantic web, and it is it makes it possible to write semantic relationships in triples, but it is not that unreadable as RDF. So RDF is unreadable for humans, but turtle is readable for humans. So we are making turtle a little bit more readable, details are not part of this talk, but anyhow, you can pretend that user can talk with agent in agent's language, which is oversimplified version of English. And that's incoming direction. And if agent can wants to return information to user, it can use the same agent's language, or it can use much different representations, more machine readable, like JSON or HTML. And we use JSON when the agent wants to return the graph representation to user, or if the agent is being integrated with some third-party software, like we integrate some of the agent services with SingularityNET right now, then we can return information in JSON, and that's the same information that can be returned in the agent's language, but we just wrap it into the JSON for readability purposes, for machine readability purposes. And also the information can be returned in HTML, and that's useful when we return a report for user, so user can view the results of the agent's operations in form of report. We will see it a little bit later. So whenever a conversationer is interacting with the user through communicator, it keeps information about the user sessions in sessioner. It keeps all information that is in the attention focus in short-term memory. The information that doesn't need to be in attention focus is going to archiver or long-term memory storage. And there is a process which does the inferences, it is called thinker. And there is a selfer which does all which controls all of these activities. And there are two specific components which are about interacting with web, so online media and social media. So SiteSpider is responsible for online media. It parses and crawls HTML sites, and social feeder is about social media, dealing with social networks, blockchains, and messengers. Right now, it's getting a little bit more complicated. So here is the another way attempt to make this architecture a little bit more straightforward, so, and track the way information is going through the system. So at the first level, we have either SiteSpider, which crawls a particular site or a bunch of sites is connected by web links. The social integrator or a social feeder gets information from a Facebook or a Google or Contact or Steemit or Golos from social networks and blockchains, and now there are Reddit and Twitter. And then there is a communicator, which is actually needed for direct interaction with user. And user can interact with the agent in few different ways. First of all, it can interact using plain chat in agent's language, in simplified English language, or the language-based or chat-based interaction can be hidden under the user interface. So there could be Android client, a JavaScript client with jQuery, and Swing client for Java user interface. And then all statements that user is saying, that agent is saying to user, and all inputs that agent is receiving from user are translated through and to specific user interface elements and actions in the user interface. So the user can be interacting with graphical user interface, but that's all translated to expressions in the agent's language. And then there is a talker who is and the reader who actually is handling all these messages in agent's language. Then if we are going to interpret the social integration information coming through social integration channels, there is social feeder. Then in order to deal with sites, there is a pattern finder, which finds the patterns of the information found on web. Then there is a what pretends to be machine learning stuff, like thinker, which does clustering, learning, and categorizing of information. And now when the results of analysis information is going to be presented to user, either we have a talker and writer, which are just sending information back to the same communicator, to the same chat or graphical user interface representations, or we have a report writer, which renders either a report in HTML or a JSON structure, and so the report can be viewed in the browser, and the graph structure can be rendered in the graph renderer. And here, what we actually have. So unfortunately or fortunately, right now it happens like everything is connected to almost everything. I can give you just example why it's so, is that we were finding that if we are trying to build interfaces and classes for the implementations of specific media channels, like whether that's a social network or a specific kind of website, there is a lot of overlaps. And I can, that's maybe a longer discussion, but we are getting right now a specific interface which describes all possible properties of a channel, like it might be partially a site and partially a social integration channel, and there may be different virtual functions which may be implemented in one social adapters representing these spiders and crawlers, and maybe not represented in others. And effectively, like for example, if you are using PayPal, right? So for example, let's say we have a PayPal adapter here. So PayPal is just a payment system. It's not social network. But if you consider a Steemit social network, it's not just a social network. It's also a payment channel. And so it has, so the Steemit can be a social network and a payment channel. And if you take a Steemit from the other perspective, the Steemit is a site. So you can consider Steemit from the perspective of individual user account, and that's a social network, or you can consider a Steemit as just a bunch of feeds under a specific tag, and you can browse from one feed to another feed, and then that works like a site. So under the hood, there are many complex and interrelationships between the different packages, but we won't cover this now. So now let's move on to the specific user cases. So the first use case that is provided by agent to user is just what I have covered before. I just quickly restated. So based on the initial learning from the user past experiences in the outer social networks, and based on the user explicit corrections of the profile and implicit free feedback from the reinforced experiential and reinforced learning provided by the user to agent. Agent can compute personal relevance, blue bars here, and it computes social relevance from the friends and the connections of the user, and based on that blended or integrated relevance, the users may be getting what is the most important and what is the least important. And when we are dealing with patterns, and when we are matching the patterns that agent learn from the users, or that users maybe explicitly tell agent to follow, here we have the definition of what we imply by pattern, and that's what we actually want, what we call model to be. So when we think about a model which can be used to pattern matching or classification or entity extraction, we assume that we want to talk not about just some binary object which can be loaded into the neural network, and then we can make decisions based on the neural network. We want the model to be explainable and interpretable. So, and the models in the AI agent system are the deep patterns. And the deep patterns, and we call them deep patterns because they may be hierarchical, and they may have multiple levels of hierarchy. and the hierarchy is recurrent. So you can define a set, and the set is a fundamental element of the hierarchical or deep pattern. And the set may be a disjunctive set, or it may be a conjunctive set, or it may be a skip and gram or sequence. So disjunctive set is just disjunction of elements, conjunctive set is just conjunction of elements, and skip and gram is ordered conjunction of elements. And by the way, the concept of these three kinds of set goes back to 20 years ago, WebMind project, where we worked with Ben Goertzel, and in current OpenCog architecture, these three sets are represented by OR node, disjunctive set, and node, conjunctive sets, and I don't believe how it's, I'm not sure how it's called now, but there is a node in the OpenCog which is representing sequential, and I believe there are a few different types of nodes represented sequential and they probably have different semantics. Probably there is ordered and the sequence, maybe something else. I'm not quite sure. Probably the guys are discussing this in the other room right now. And then and okay, so here how we record them. So disjunctive set is recorded with this kind of brackets, conjunctive set recorded with this kind of brackets, and here is the way how we record skip and gram. And then the pattern is either a single token or keyword, or that's a regular expression, or it's a set, and the set is defined earlier, or it's a variable. And the variable is what is called slot in the entity extraction and conventional dialog flow designs. And this variable is effectively some variable which can be filled. And by the way, that's quite, in terms of OpenCog, that's also called variable or variable node. And these variables, besides just having a place within some pattern, they may have domain restrictions. So each of the nodes can also have specific domain restrictions applied, and so you can make sure that this node is actually passing these restrictions when we are matching the pattern against the text. And here is example. For example, we are building an application that needs to extract some medical care items like different sorts of catheters from the text in English. And the catheter has description. And here is the variable for description. And that variable is indicated with the $sign. So whenever you see the $sign in an agent's pattern, that's a variable. So the catheter has a coating, inner diameter, tip, and the pattern of a catheter, not a pattern of the agent's deep pattern. And then here's the pattern which says that first we have any of these items to be appearing. So we have a disjunctive set of any of the ordered sequences of any of the n-grams. And each of these n-grams may be either variable of the description and catheter, a variable of the coating and coating, variable of the inner diameter, and then either diameter or inner diameter, etc. And then if we take the plain text and apply this pattern to this text, we are getting the object or subgraph where we actually have the values of the links filled with this subgraph. So given this JSON statement, we can create a node like catheter number 352 and link coating to hydrophilic, link description to convex guiding, link pattern to ultra thin, etc., and link tip to soft. So we have identified the object and we created semantic subgraph represented this object. Another element of the technology, and that's the place where we have most of AGI or narrow AGI at this point is what we call targeted adaptive search. So it solves the problem of the adaptive web navigation, and it solves it just within the framework of the definition of the artificial general intelligence that we have seen on one of the first slide. So it has multiple goals. So the agent may be given multiple patterns. So we have multiple goals. Then the agent have complex environments. It has multiple links, multiple source. Sorry, it has multiple sites to start search with. The sites may be written in different languages. They may have different design, HTML design patterns, or maybe even different style sheets, and there may be different ways of structuring the information on different websites, and the agent should be able to find the balanced subset of the information, minimizing the resources, avoiding overconsume the search and monitoring time, so the user that gets the information, but the battery on the smartphone is not overheated, and the smartphone just doesn't die because of the dense information search. For example, if the agent is running on the smartphone. By the way, by design of the agent, it may run on any environment that is capable to run Java. Like if you want to have your agent stored in the cloud, you can just register your agent on the eagents.com website. And then the privacy of the information will be provided just with your by means of your agreement with us, with providers of the eagents.com website. On the other hand, if you want your information storage to be private, you just install the eagents software on your own server, and then you take care about the privacy of the information. So all the search and all the monitoring is being executed on your premises, and you can share the access to this server based on your own company or group information security constraints. Finally, if you are a personal user and you don't want this information to be stored anywhere, you can run just on your own smartphone or on your own tablet. Unfortunately, currently available version for smart Android smartphones and tablets is outdated, so it doesn't have all latest bells and whistles for the social integration, but we have plans to upgrade the Android mobile agent version soon. Now, here is another case of how we want agent to be trying to help users to improve their, by the way, so as I was talking, so where we have some initial steps of the AGI development here is we are implementing adaptive navigation using the definition of the AI. So the algorithm that is building to logic or schemata guiding the agent to run through the different websites, and we are using different and multiple pages. It tries to memorize context. It tries to memorize the chains of different contexts that were leading to the goal. And if agent memorizes that the particular sequence of contexts is actually succeeding, it memorizes the sequence of contexts where the each of the context is specific web page and specific link from this web page and the next web page which is behind the link. So each this transition following specific links with specific text is considered as a context, and the chain of context may be either leading to your goals or not leading to your goals. And if the specific bunch of paths are confirmed leading to the goal, then the paths are memorized and then exploited in the next search and monitoring operations. And if at some point the agent realizes that none of the paths memorized in the past for a given goal is not succeeding, then it may switch from the behavior utilizing the previous knowledge to exploratory logic. And in exploratory logic, it tries to find the new paths instead of utilizing the previously known paths. So here, back to the case 2, we are trying to render the information that the social side of the agent could be using in order to improve people to improve their social performance. So, when the agent studies the activity of the users online, they, for example, can mine the posts for the words that users are using, and the words that users are using in these posts, and amount of likes associated with the posts that users are making. And so it can do the inference which of the words may be more attracting for the other people, so they put their likes or votes on these posts. And it can also understand which people are making the likes or votes, upvotes in respect to these specific words, and it can render the historical graph or histogram of the change of the karma or reputation over the time. And so you can see, like, for example, on this picture, on particular period, I was, and that's, by the way, the report made for me just by myself, I was seeing that at particular time period, I was saying something about OpenCog, and I had attracted the karma or reputation at level 67. And here are the people who was most contributors for this particular period and with this particular bunch of topics, and I can know who are these people, and so I can make some decision that if I want to talk more and to be more saying more about the same topic, I can be attracting these people to help me share this information in the in the subsequent communications. How it works in real time. So when you, if you are using web version of the AI agents, then you can log in with your or register and log in with email, or you can log in and register with any of the social networks, like it is Google on this side. Unfortunately, Google Plus social network is down right now, but you still can register with Facebook, with Twitter, with Reddit. You can plug into your Steemit social account. And with each of these social network, whenever you register, you can get your social network, social report. So you can get all what is possible given specific social networks. All social networks are different. Like if you use Steemit or Golos, these on blockchain, then you can get whatever you want because these social networks are public. For the opposite, if you use Facebook, you get almost nothing. So very recently, Facebook has just closed almost any possible way to use the information that you store about yourself or yourself online. So the only little thing that you can get on the Facebook right now is just posts that you are making yourself in your own news feed. So we can still use Facebook to mine the profile in respect to interests of the user, and we can find the URLs, we can find the patterns, topics that user likes, but we can get any social interaction information from the Facebook. When we use Twitter, Telegram, Reddit, and Steemit, then we can get much more useful social information. Anyhow, whenever the information is obtained by agent, you can use review your profile, and you can review the dynamics of your profile and your social performance over the time, and you can also browse this information in the graphs. So you can use graphical representations of your social environment, who is similar to you, who are your followers, who are your supporters. So here is just an overview of how we do that. So we have the user of the agent, we have the friends of the user. And then there are some topics, and there are some relationships between the people and between the posts and comments and between the words that are in the posts and the comments. And there are calendar periods that are framing all that. And we can use some math, and using this math, we can just do inferences of the new relationships, like my own interests my friends. So then based on that, we compute similarity, we compute who are best friends and colleagues, or rather fans who like and comment me, or rather authorities or opinion leaders who are liked and commented by me, my posts, my favorite posts, my posts liked by the other people, etc. And we can also attach this dynamic to specific periods and watch the dynamics over time. Another sort of analytics that we can that the agent can do about a person and tell the person as a report, and in the future we anticipate it could actually use this information in its own predictions and recommendations, is about social structures involving the people and social patterns of the people themselves. Like on the top left corner, you see kind of person who is follower, who have a lot of people who it comments to, or who the person likes. At the bottom left, there is a social type opinion leader, who rather is not liking or commenting anyone, but it has, or she or he has lots of comments and posts and likes and votes by others. And on the right, we have two different sorts of people who have both opinion leaders and followers. So there is social type peer, who has a lot of peers with the same level of attention or social reputation, or it has a few opinion leaders with the reputation level above the person, and a few much more followers who are below, who have lower level of the reputation. By the way, what we see on vertical axis here, so the vertical axis on these graphs correspond to local reputation. By local reputation, I mean that the fact that the person is at the very top of the chart means that within the subgraph of given user, this person is the most highly reputable. And that doesn't mean that this particular person is not highly reputable within the community. So in order to get this, we need another kind of computation. Another case here is that we can actually browse the graph. And when we browse the graph, we can start from some point at the very beginning, and then we start clicking, and clicking on any node in the graph, we are getting further, and we can traverse the graph until we reach some ultimately highly reputable person or opinion leader who is actually maybe just driving the entire community. And what is interesting is that in if the environment that we are using have a lot of different relationships, then we can actually explore the social structures using all these sorts of relationships. For example, when we do analysis applied to STIMIT or GOLAS social networks on blockchain, we can study 3 different sorts of relationships. There are comments, there are posts or likes, there are comments on posts, there are likes or votes on posts. So the votes on Steemit are what are likes on the Facebook, and there are also payments. For example, here we see the structure of some small community, and this community is structured into few subgraphs. And one subgraph in the middle is based on the payments. So the green arrows on this subgraph correspond to payments. And on the right, there is another subgraph. We involve in different other people. And this subgraph involves comments, and which are blue, and likes or votes, which are gray. So here is the people in the middle are just sending money to each other, and people on the right are just communicating without sending the money each to other. And on the left, we see three different tables, which briefly represent different sorts of social analytics. Like on the left, there are fans or followers of particular person. In the middle, there are authorities of particular person, and it happened to have just one authority Steam board. And in the bottom, there is a reputation in community. And here is non-local reputation, and non-local reputation assumes computation of the reputation within the entire community involving all users using the weighted liquid rank reputation algorithm that we are developing at SingularityNET, and it makes it possible to include the interaction within the all entire community, all scope of the reputations recorded in the online social media environment, to compute the reputation based on the ratings. And when we compute the rating of a person within the liquid rank algorithm, which is rendered on the right, when the rating is computed for a person, then the rating is based on the value which is given with the rating, but also the reputation of the rater who provides the rating is accounted as well. And the reputation of the rater itself based on the ratings given to the rater by the other raters, and this rating is based on the value of the rating and the reputations of these raters. So the reputation is flowing from the first rater to the final ratee or the person being rated through the all possible paths through different participants in the network. It's quite similar to the way Google rank or uses page rank algorithm in order to rank web pages. But what is different in our weighted liquid rank algorithm designed by SingularityNET and implemented in the eAgents product as well, is that we apply weights to the ratings, and the weights may be based on different things. And one of the way to weight the rating is amount of financial cost that the rating is associated with. For example, if the agents are providing some conducting some financial relationships, then the rating may be weighted with the actual amount of money spent by one user interacting with the other user. If the rating is implicitly provided by the comment, then with text written by a user, then the amount of text may be considered as a weight. So if I just tell something short like hi or okay to someone else, that's one story. And if I write some exhaustive analysis to the other person, then it does mean that I spend more attention to the other person than just sending a single word to the person. Also, the sentiment may be accounted as well, but sentiment assessment is another kind of forms which has its own complexities, and it doesn't worth going to talk to it in our current scope. So if we mention the proof of reputation implemented with our weighted liquid rank algorithm, it's worth noticing that it makes possible use the reputation computation capabilities of a single agent node as a ground for creation of new generation of the blockchains or distributed ledger systems based on what we call proof of reputation consensus. Many of us know that the modern distributed ledger systems and blockchain systems in particular are based on different sorts of consensus, and proof of work consensus in blockchain corresponds to forces power paradigm used in human communities. So like ancient societies were using the power of alpha males to drive the community, then modern blockchains are using amount of computational resources to take over the consensus within the blockchain systems. Now it changes. So more and more blockchains are implementing modern paradigm employed by human community. Modern human communities reside not on a power, are grounded not on a force of power, but they are grounded on a force of money. So the more money you have, the more power you can buy, and so the more order you can direct to everyone else. And so the proof of stake sort of consensus in the modern blockchains is actually the same as money as power in human communities. And it actually has the same problems. So if you get a lot of money on a blockchain because of your stake, then you are just getting more money, and then you are getting more and more options, and it's easier to you to take over the whole consensus. What we believe is good about the proof of reputation is that it is quite difficult to take over the consensus with proof of reputation or liquid rank design, because you need to actually have a long history of the interactions, and you really need to have real supporting audience, and you need to have not just multiple supporters in order to get a lot of reputation. You also need to have a high multi-layer hierarchy of supporters under your account. And here is the example that we have obtained applying the reputation weighted liquid rank reputation consensus for the case of marketplace. So what we did, we tried to build a simulation modeling of the SingularityNET, of the Amazon marketplace. So we considered multiple agents. Some of them were sellers like Amazon, and some of them, most of them were buyers like Amazon. And we split the sellers in two categories and buyers in two categories. So some sellers were honest sellers, and some buyers were honest buyers, just selling some goods with different qualities and buying these goods with different qualities. And when they were buying the goods, they were providing the reviews or rating for these goods, and the ratings were organic. So if the good quality of good was high, the rating was good. If the quality of good was low, the rating was low. But we took another category of suppliers and buyers. So we had fake suppliers or dishonest suppliers who were actually hiring the armies of fake buyers. And the suppliers were selling low quality goods, and they were paying money to dishonest buyers, and dishonest buyers were always providing excellent ratings or reviews to the junk quality goods. And then we have tried to see how different designs of the reputation systems were able to let honest suppliers, honest buyers, to avoid getting these artificially highly ranked junk quality goods. So here is the result that we get with weighted liquid rank reputation system, and the results were much better than any other reputation system design like the one that is used on Amazon right now. And so we can see that almost every honest supplier on the right is above 75% reputation threshold, and all except one dishonest suppliers are below the 50% threshold reputation watermark. So we can definitely solve the problem identifying honest and dishonest suppliers on the social network or on the environments, on the marketplaces, and we hope we can do that in the other social environments online. So here's the roadmap that we went through. I just put it in case if someone have any questions. So we have lots of developments to happen in the future. Right? For example, right now we are advancing with Twitter social analytics. We are improving communication, agent communication skills. Like one of the projects that we are talking right now, we are trying to extend the natural language support from using agents language, which is controlled English language, Unfortunately, using some experiments with real customers, we have found that for most of the people, it is quite difficult to simplify the English language to controlled English language. It's not natural to converse in that way. So right now we are doing some research on how to improve the conversational skills so the people can at least ask questions in English, and then English is translated into the controlled AI agent's language, and then agent is responding in agent language. So that's a kind of complexity, second level of complexity. The third level of complexity that we are exploring is that when the answer is created by agent, it could be also translated into the English. So even the deep inside the agent's skull, it responds in controlled agent's language, but then this language is translated to human language using the link grammar technology. And by the way, in the project that we discussed, that we presented last year on the AGI 2019 conference on unsupervised language learning, about ability to learn formal grammar structures like link grammar based on supervised linguistic corpora. That's research is also considered to be implemented in this framework. Another direction of the work that we are considering is employ the same unsupervised language learning technology so the agents can learn better patterns. So right now, if the agent is given lots of text in the user past experiences, the agent is capable to build the topics of user interest. But the agent is barely capable to actually create precise patterns like the ones that I have shown you about catheter. So right now, the patterns that agent can learn are mostly different sorts of disjunctive sets, and disjunctive sets based on the keywords, and then as experiments show, these disjunctive sets are honestly pretty stupid. So what we are looking for is like in the past last year, we have managed to use deep neural network to learn for some grammatical patterns based on supervised corpora, and then we were able to extract the link grammar structures, disjuncts and connection and associations between words in the link grammar formalism from the deep neural network, BERT in that particular example. So we are considering that it might be possible to also employ similar approach, and when the agent is learned on lots of text with that correspond to particular topics already identified by agent, then we should be able to extract the patterns from the deep neural networks specific to these topics and extract the patterns in symbolic representations, so the users could be able to review these patterns referring to symbolic variables, sets of different disjunctive or conjunctive or ordered nature. So that was my presentation. So there are some resources. So lots of references of the AI Agents project can be found under this link. So here is my email and contact information. So the demo AI Agents application can be found on the aiagents.com website. It should be noted that that's just a demo, and the end-user interface based on the web query, so based on the Java query, is appears not quite nice. So that's we have just for demo. So we are looking for to change the user interface, but user interface is just a thin JavaScript client on top of the AI Agents language. So if you use AI Agents language and if you interact with AI Agents server over the AI Agents language-based API, over the HTTPS protocol, you can get much more functionality that is present on the aiagents.com website, and you can actually take the open source on the GitHub and install your own agent server, and you can use your own interface on top of it, or you can create any client of your own on top of that agents language over HTTPS protocol. And we have lots of videos and updates on all sorts of social media. And that was my presentation. So if you have any questions, I am happy to answer them, or maybe show some code or some functionality on the web. Thank you.
Awesome. Thank you very much, Anton. Yeah, so if you have any question, just yeah, ask ahead. Okay, seems like there are no questions. I'm just checking whether our next speakers, I think Matt and Neil, let me just double check. Yes. All right. We will enter a short break right now while we are switching to the next speakers.
Okay.
Thank you all so much for watching, and we will be back with you in a minute. Since we have finished a little bit earlier today with Anton's tutorial, we will be seeing you back at 12:30 Eastern Time for probabilistic reasoning and pattern mining using OpenCog.
Hello, everybody. Can you hear me?
Yes.
Yes.
Okay. Maybe I should try to share my screen to see if that works.
Yep, go ahead.
Okay. So let's see. Does that work?
Yes.
Yes.
Okay, great. Okay, then let me try to. So, okay. So now I stop and I try to share, I guess. Share. No, that's not what I want to share. So yeah, okay, I see what you're saying. You're seeing a terminal.
Yep.
Okay, so let me try something else. Okay. Share. So now you see another terminal, but that's the right one. Okay.
Yes.
All right.
Your webcam is, by the way, a little bit low, so if you want to
Yeah. Well, I mean, the thing I don't think you're gonna see me very much. I don't intend to keep a static position. So, yeah. I mean, yeah. Blah. If I really have to be in front of the camera, I'll adjust. Okay, so I can stop sharing that, and I'll go back to. Right. So Matt, I went with something like I have an hour plus of tutorial, and then I thought we just leave room for discussions. I mean,
Yeah.
like the tutorial is really stuff to do. It's not me present. I mean, well, I'm going to present stuff, but there's as well stuff to be done by the participants. And then I can show you more stuff if we run out of time, or we can have a discussion. I thought.
Sure, yeah. You are the last, I think, to present for today together with Matt.
Mhm.
So, yeah, take. I guess you can take your time.
Pardon me?
You can take your time.
Right. So, yeah, I want to. Okay. Do you hear some background coming from me, like voices of children?
Mm-hmm.
You do hear that?
A little bit, but it's not disturbing.
It's not disturbing?
No.
Okay. It looks like well, that's the time is now, right?
Yes. Are you ready?
Yep.
All right. So we will have a tutorial about probabilistic reasoning and pattern mining using OpenCog with Neil Geisweiler and Matthew Eichel.
Thanks for the introduction, EB.
Thank you.
So the plan for for this tutorial. First, we're going to have a little bit of preparation that we're going to do first because it involves downloading a Docker image. So better do that. And first, and during this time, I'll give a little presentation that are going to help participants to understand the notions that are being presented during the tutorial. And then I'll go on with the tutorial. And at the end of that, we can have a discussion, or I can show you more stuff. Yeah, it's kind of, it's open-ended. So the first thing you're going to do, if you want to actively participate, you're going to have to install Docker. And once you have installed Docker, you're going to pull do you see the my mouse cursor? Do you see it?
Yes.
Yep. Okay. Right. So that's the instruction for Debian base and Arch base to install Docker. Well, if you have something else, I can't help you. And once you have installed Docker, that is the command line to download the image. If you happen to already have OpenCog installed on your system, I don't recommend to use it because actually in the last moment, as I was preparing the tutorial, I found a few bugs and I didn't have time to create proper fixes, and to merge them into the master branch. So I have works around, but they are on the Docker image, but they are not on the master branch. So yeah, so better if you just go with the Docker. So the command line to download Docker will be displayed at the bottom of each slide, so I can move on. Okay, so right. So the tutorial is going to be about OpenCog, as you know. We're going to focus primarily on reasoning, but I've got to give you a little bit of a recall about OpenCog. So it is a framework for AGI. The thing that the crux of it is that there is a central database, which is a hypergraph or metagraph, which is called the atom space. And on this atom space, we have a language called Atomies that can be used to query this atom space. It can be used to rewrite the atom space as well. And so that's the core of it. And around this core, we have cognitive processes that we call mind agents that can operate on this atom space. So for instance, that can do some reasoning or some learning, maybe some data mining and so on. And as Ben mentioned in room 2, this is via this atom space that we can enable this cognitive synergy because they have this point of contact, which is the atoms in the atom space. So yeah, I mentioned atoms, so I'm going to have to explain what that is. So an atom is basically an element of this atom space, which can be a link or a node. And the particularity is that a link can be connected to a link as well. What else can I say? Yeah, so he's doing a bunch of stuff, like even natural language processing and stuff like that. But here we're going to focus on reasoning. Okay. So the primary logic used to reason on the atom space is called PLN, for probabilistic logic networks. It was invented by Ben and Matt and a few others. And it has a few qualities. First of all, it is based on probability theory. I mean, one might say probability theory plus, because it incorporates, it goes beyond that, but the foundation is really on probability theory. It has, it incorporates representation and management of uncertainty. And the interesting thing about it is that this uncertainty is also grounded in a probability theory. I'll talk more about this. It is rather suitable for common sense reasoning, but can also be used for mathematical reasoning. And it can also be used to reason about resource management. And that's how we can do some form of meta reasoning, which I'll briefly talk about. So I'm going to go straight to the basic. So how do we represent probabilistic relationships in PLN? Well, we have this link here, subset, and what subset AB says is that we have a certain probability of B knowing A. I mean, that's essentially what it is. So subset is the notion of subset in set theory, but the thing is that we have this probabilistic and even fuzzy probabilistic variation on it, which allows it to have a semantics, a probabilistic semantics. So what that means, so this what you see here is atomies. I mean, this is what we write in our atomies interpreter, or whichever variation we use to enter this knowledge into the atom space. This thing here is the truth value. STV stands for simple truth value. Okay, as I said, the subset of AB represents the probability of B knowing A. S is the strength, which is the probability itself. And C is the confidence, with some formula, which, I mean, doesn't really matter what is the formula. It only matters that it's a monotonic mapping between the number of observations and the range 0, 1. Whoop, let me. Okay. All right. Any questions so far? If I don't hear anything within the next 5 seconds, I'll move on.
So I think, Neil, you mentioned the confidence, and you can also map confidence to the evidence, the gathered. So there's a back and forth one can do.
Yeah. So that's exactly what I was saying. So the size of A would be basically the number of observations. And so, as you can see, when the number of observations is growing, this thing is gonna tend to 1, right? And I mean, okay, I'm gonna move on.
Yeah, that was all I just want to just mention that there was this correspondence.
I mean, yeah. So that's exactly what I wanted to present next. Is that the interesting thing about a truth value is that well, I mean, okay, STV stands for simple truth value, but why simple? Well, as you guessed, the reason is because there can be less simple or complex truth value. And why is because a truth value underneath is actually a second order distribution. So as I was saying, that uncertainty is grounded in probability theory. It's really this. It's that when we talk about a truth value, we are talking about a probability of a probability. And so here are some examples of distributions of these second order distributions. The first two would be the case where we know absolutely nothing. So there is something, there is a pattern, whatever. There is an event and we know absolutely nothing about this event, and it could have a certain probability. And if we don't know anything and we take a Bayesian prior, then this probability would be completely flat. If we take a Jeffers prior, the probability would be slightly concave. And as measured as we accumulate observations, we're going to narrow down this distribution to something, well, more precise. And if we go to infinity, we get a Dirac distribution. Okay, I mean, it's all well and simple, but this actually is only true if your second order distribution is a beta distribution. And that works well, but in some cases you need to go beyond that. And so when you need to go beyond that, well, you need to resort to more complex truth values. So as you've seen, a simple truth value is two numbers, is characterized by two numbers, a strength and a confidence. And a beta distribution is characterized by two numbers, alpha and beta. And so that works. But as soon as you start to do some reasoning, or you start to aggregate knowledge coming from different sources, then the beta distribution breaks down a little bit. But overall, that works well when you just want to account for observations. Yeah, direct observations. So where are we? Okay, so any questions so far? Okay. So here's an example, for instance. Here we have this simple knowledge base. Okay, we have probability of B knowing A is this, probability of C knowing B is this. And we know that A is true with a certain probability and confidence. And we can use these rules. So here it's a deduction rule. So knowing, well, sometimes I'm going to say, so the thing is that there's actually, I mean, this notion of subset is actually isomorphic to a notion of implication. So when it's convenient, when it flows well, I'll say implication. And so we could read this rule as if X implies Y and Y implies Z, then X implies Z. And of course, it's true to some degrees, and that's going to depend on the truth value here, and well, this one is going to be calculated by the rule. So here we have the modus ponens, which has been again probabilitized. If we have if X implies Y and we have X, then we have Y to some degree. Okay, so what can we do when we have that? Well, we can basically plug together these rules to construct inference trees or inference graphs to prove things. So given certain some axioms or some knowledge base, and given these rules, we can start to ask questions, or we can simply run the system in a forward manner and just ask it to infer all possible theorems. Oh, sorry, I have. Yep, I have to. Okay, so that's what I was saying. So here's a simple example of an inference tree. So given the knowledge base that we have here, is it this? Yeah. Given the knowledge base that we have here, how can we infer the truth value of C? Well, we can construct this inference tree that first construct the implication of A and C with a certain truth value. And given that we have A with a certain truth value, then we are going to be able to infer C. Okay, so that's a very simple example. But basically, I mean, PLN, it might look intimidating when we look at it the first time, but actually it's rather simple, because it is really constructed on this simple probabilistic / uncertainty rules. I mean, it's everything else is just built on top of that. So I mean, it's more subtle than that. For instance, we have, when we start to get into universal instantiation, I mean, we do need to quantifiers and things like that. We do need to invoke a third order distribution, but apart from these subtleties, it's really just based on these simple things. We have also intentional reasoning, which is also based on that. Intentional reasoning is extensional reasoning, classical probabilistic reasoning, but instead of using the sample space, instead of using members, observations, we are using a sample space of patterns. And everything else is, we also have the notion of contextual reasoning, but all this can be mapped into the basic form of reasoning as well, and so temporal and spatial. Okay. All right. So, of course, reasoning is nice, but the problem is that it's generally inefficient. And in order to have efficient reasoning, so basically PLN is implemented on top of what we call the unified rule engine. And this unified rule engine is able to accept control rules to guide the inferences. Now, the interesting thing is that these control rules are atomist code. So basically, because of that, they can be learned, they can be reasoned, and this enables some form of meta reasoning. So the most simple case we have for a control rule is a context-free control rule. So basically, it's equivalent of having a weight on the rule. So an example would be, for instance, okay, let's choose deduction 90% of the time and modus ponens 10% of the time. And it can help, but it's not going to go very far if the inference starts to be too complicated. Something that can be really powerful is a context-sensitive control rule. where we relate the rule to, well, the fact that we are going to have a successful inference, but also the context. And so this allows to dynamically adjust the weights of how we're going to choose the rules to efficiently guide the inference. What else do I have to say about this? Did I forget something?
I think this is good. I mean, we can go into further depth on that later on,
Yep.
but
Okay.
I think at this level, this is good.
Okay. All right. So, okay. So now we have the pattern miner that comes in Y. Well, there are different reasons, but first of all, the pattern miner is one way. Well, I mean, why do we need to mine patterns in the first place? So one reason would be to just learn context-sensitive control rules. For instance, we can learn a bunch of inferences. I mean, we can just run a bunch of inferences, and then we keep a trace of these. These traces, they live in the atom space, and so we can mine these traces, and we can start to build this sort of context-sensitive control rules. And to relate the context to the rule and to the fact that it's a successful inference, the pattern miner can help. And the thing is that the other related aspect is that the pattern miner itself is actually implemented on the rule engine. So it is a form of reasoning. It's not completely, I mean, it's not a fully transparent form of reasoning, although it could be in practice. But yet the interesting thing is that because it's a form of reasoning, the pattern miner itself can benefit from learning inference control rules. And so this is really an example of fully recursive meta reasoning, where basically the only limit is as long, I mean, if whatever control rule you learn is abstract enough, if it's abstract enough to apply to your problem, well, it's great. But if it's even, if it's so abstract that it can even apply to your problem of minding inference control rules, well, then that's great. Because in one shot, you just, I mean, you can go to several levels. Of course, I mean, there's a catch, which is that the more a control rule is abstract, the less predictive power it's going to have. I mean, that's typically the case. I mean, the only way to have a good predictive power is to basically consider restricted domains. As long as if you start to consider everything, the whole universe, then it becomes very difficult to have strong predictive power. But nevertheless, so okay, so let's go back to the pattern miner. And so here's a simple example. So we have these relationships in the atom space, and well, we can see visually that there is some pattern, and we can run the pattern miner to discover this. So for instance, we have, so okay, let me explain. Patterns are called, in fact, frequent patterns because they have to be frequent enough in order to be accepted. And so if we set the minimum frequency, I mean, the minimum count to 3, then we do find that this particular pattern, well, A is a subset of B or a subset of C or a subset of D. Well, it's a subset of something. Okay, that's a pattern. We have another pattern, which B is a subset of E, and C is a subset of E, and D is a subset of E. Well, something is the subset of E. Okay, that's another pattern. And we have this pattern as well that combines the two, where A is the subset of something, and this something is the subset of E. Okay, so these are the kind of patterns that we can discover with a pattern miner. All right, so, okay, so that would be like the most generic, greedy pattern mining algorithm, which I don't really need to explain in detail. It's the main thing is you start with the most abstract pattern, and you see the if it's frequent enough. Well, if your database is big enough, it should be frequent enough. It's because it captures all the instances of the database. And from this top pattern, you start to specialize, and you check if the specialization is frequent enough. And if it's frequent enough, you keep it. If it's not frequent enough, then you discard it, and you don't need to explore any subsequent specialization of it, because, well, if that one is not frequent enough, any specialization are going to be less frequent. And so that allows you to prune the search space rather effectively, depending on the minimum support that you consider, the minimum count. Okay, so basically I said that the pattern miner was actually implemented as a form of reasoning. So how do we do that? Well, we basically take this simple property, which is called the a priori property, which says that if a pattern is frequent enough, then any abstraction of this pattern, let me read that. I don't want to get confused. So Q is the specialization of P. So P is the abstraction. And right. So the premise is, if some pattern is frequent enough, then any abstraction of this pattern is going to be frequent enough. All right. And so we take this rule, and we start with the top pattern, and then we run this rule backward, and we generate the specialization. And if the specialization is frequent enough, then we can keep going backward. And if it's not frequent enough, then we stop. All right. So, right, but so frequency, I mean, pruning by frequency is nice and efficient, but the problem though is that depending on the cases, you might still have a lot of patterns, and there might also you might just not discover patterns that are frequent enough that seem to be useful. And when you lower the threshold of frequency, then you get tons of patterns, and you don't know how to sort out what's interesting, what's not interesting. And so on top of that, we have a notion of surprisingness, a measure of surprisingness, which is also implemented as a form of reasoning. Basically, I mean, this notion of surprisingness really could be anything you want, I guess, but here in our case, we have used a distance between the truth values of the patterns that we are mining, and it would be so the difference between the empirical truth value and the estimate. So the estimate is basically how would you expect that this pattern would be doing under your assumption of the world. and the empirical is how it's actually doing. And so if it's too different, well, then it's surprising. So how do we represent that as a form of reasoning? So let me check the time to see if I'm not drifting too much, because you know when you give it. Hey, I'm realizing something. You are, because this. Wait, that's very confusing. I mean, I suppose you are seeing my slides because you would have told me otherwise. Because Zoom is showing that on another screen. Okay, I was slightly worried that Zoom was playing a trick on me, but that doesn't seem to be the case. So, okay. No, very odd. Okay, anyways. Yeah, okay. Okay, I've been doing that for half an hour, am I correct?
Mm-hmm.
All right. Okay. So I don't know how much I should detail of that. But I can show quickly. So we have the surprisingness here, which is what we want to assess. And here we have this notion of distance. It's a Jensen-Shannon distance, but really it could be something else. Here we have the estimate, here we have the empirical. And the interesting thing about this, when you frame that into reasoning, is that in order to get the estimate, to infer the estimate, well, then it becomes an inference problem. So there's an infinite way, there are infinite ways to estimate that. To estimate an estimate, it depends on what you know, it depends on your assumption about the world, et cetera, et cetera. By doing that, basically it opens the door to, for instance, a more dynamic surprisingness measure. That is, you saw something first, it wasn't looking very surprising, but then, well, you have updated your model of the world, and then you can take this into account, and the next time you see something that relates to it, it will be less surprising. So it's a very powerful way to measure surprisingness. Okay, well, that's, it's a work in progress. We are scratching the surface at this point, but it is certainly promising. Okay, so we can move on to the tutorial itself.
No, I think this would be a good time. There's a couple questions, or right, at least that came up on the chat.
Okay, great.
So I think Mike Miller has some a really good question about the knowledge base and rule set, whether it's synthesized by another program or is this hand constructed. I can answer, or I'll let you answer either way.
Yeah, you can go ahead if you want, and maybe I can complement.
Well, so I think there's two questions there, right? There's the knowledge base, which is essentially, if you think about it, it comes from experience. As you gain more knowledge, so the knowledge base is not manually constructed, but the rule set, it is probability theory at an underlying level. So at this point, at least, and that's why I kind of really wanted to address it. Like the deduction rule is based on the standard probabilistic deduction rule at some level. What's different is its reasoning under an uncertain world. But I think the interesting part is, how do patterns pay into construction of rule set? Is that something when we talk about meta learning?
Yeah. So I didn't mention that, but the rules are actually described in atomies. So, I mean, as of today, actually, they are not 100% described in atomies, but we can nearly do that at this point. And so basically, yes, they are hand coded initially, but then it's possible to enable the system to learn them. And in fact, it will probably be really desirable. I mean, when you think of deduction, for instance, yeah, deduction works well under some assumptions of independence and so on. But if you start to, if you want to go beyond that, well, the deduction rule is gonna, it's gonna grow in complexity, or it's gonna be more open-ended, and it's gonna be needed to be, you're gonna need to plug more stuff into it. It's gonna have more premises and so on. And there's a trade-off which is just not easy to get by hand at this point. So having the possibility to learn them is obviously a good thing.
Right. So in terms of the actual theory, I mean, the base layer is based upon human knowledge, right? The probability theory.
Right.
But then we're building different pieces. And I think atop that, and that's where the meta learning comes in, the surprisingness for learning, discovering new patterns. And another thing that I think and maybe I don't know, because I didn't go through the talk with you beforehand, but the inference complexity, which you touched on in terms of context, I think at some point, I don't know if you're going to be talking about the cognitive synergy aspects and how that would play in for reasoning as well at some point.
Yeah, so I mean,
the end.
Yeah, yes, I'm done with my presentation for now, but what I can say about this is that, I mean, there are certainly, I mean, each learning algorithm has its own biases, and obviously some are just more amenable to get off the ground, basically. I mean, they might not be very general, but they're general enough to learn some useful patterns about the world, or about I mean, the inner world, the control of the system itself, and so it's a nice thing to allow these more specialized, well, not necessarily more specialized, but these learning algorithms with their own strengths and weaknesses, to allow them to basically give what they have to give before there is a more full-on, just completely self-rewriting, completely, I mean, self-aware, self-rewriting, etc. system that would then, I guess, eventually don't necessarily need these algorithms anymore, or is going to create its own algorithms. Yeah, I don't know if.
Okay.
Yeah.
I don't see any other questions on the chat. Any questions from anyone else?
I have one question. Do you hear me?
Yep.
It's about the possibility that, as you said, there are some basic, maybe some kind of building basic blocks, logical, probabilistic logical building blocks within the system, and system starts to work on some kind of application, for some kind of application. And is it possible that along the way, these building blocks, these basic building blocks, enable some kind of embedding of this very specialized, some kind of new type of or very specialized logic for this application, some sort of embedding of something which is not programmed or built in the first place?
I'm sorry, there's a word I didn't understand. Did you say embedding?
Yes, embedded application-specific logic for, yeah.
Yeah, so I think ultimately it has to do that because, I mean, like even the control rules, I mean, okay, it's nice, you have control rules, you have a lot of knowledge, and you get better at choosing the next rule to apply in your inference. But the thing is that you're going to accumulate rules over time, and then at some point, even choosing a rule becomes extremely costly. So then, okay, well, we have ECAN, we have attention allocation, but at some point, this attention allocation also is going to blow off. And so at some point, you need, I mean, there's just no way around that. You need to turn this machine into some, I mean, it needs to be able to turn some of its parts into just, you know, more automatic, just algorithms, just code that is, we know that it's going to do well, and so we can just turn all these complex interactions into some simple code that is just going to do well in this context. And I mean, it's very much like our autonomous behaviors, the way, I mean, we walk without thinking about it, etc. So I don't know if that was your question, but
yeah, that cleared a lot. So there is a possibility that something like this basically grows on itself without autonomously in some certain way.
That would definitely be the goal. I like Nils' example towards the end there. Yeah, we as humans, we learn to walk and run and jump. But then occasionally you trip. And every time you come across one of those examples of tripping, say, you learn, you get better, you modify, and hopefully it begins the takeoff, right?
Yeah, so
it never becomes totally automatic. It becomes totally automatic until it doesn't.
Yeah, so I mean, the way I see it is that there is some sort of Uber planner that is able to notice that some parts can be automatized, and so all these can be orchestrated, I believe, via reasoning. Yeah, I mean, I think the Gödel machine is a good conceptual framework to think about this. Yeah, I mean, it's we're not there yet, but I think it's the direction that it should go.
Thanks, thank you.
Or at least it could go. So okay, so now I'm gonna unshare the screen to share another screen. So I'm gonna have to find. Really odd. Okay. Okay, I think I got it. So I need to have Zoom. Oh, okay, interesting. Okay, so now you should see a terminal with some Docker command. Right, okay. So assuming that you have downloaded the image, now we're gonna run the image. So like, should I press enter right away, or do you want me to, maybe I should let a little bit of time for others to type the command. I'll give 1 minute maybe. How are we evaluating this call? Is there anybody trying to follow along, or?
Yes, we have someone who's very enthusiastic on YouTube called Andre, who is following along step by step, and he cannot wait for your next instructions.
Okay. All right, great. Oh yeah, excellent. Okay, so I guess I'll type enter, and yeah, if someone wants to go back to it, I guess I'll go back to it. Okay, so now I'm inside the Docker image. So I've installed Emacs, Vim, BioBoo, Less, Nano. I think that's about it. Screen as well. So I mean, I'm entering Emacs, but anyone can stay in the terminal. It's fine too. But the thing is that having Emacs or BioBoo or Screen just allows to see a README as well as entering commands, so on the same screen. So that's why I'm doing that. Okay, I'm gonna enter in the current directory. We've got this file, AGI 20 PLN tutorial follow along. It's a markup file. So, okay, I'm entering this file. And I'm gonna have a shell in the other window. All right. Right. So if you want to use, I mean, if you are familiar with one of these tools, well, it might make the tutorial easier. Otherwise, you can just stay in Bash. Okay. So the first thing we're going to do is enter Guile, the Guile interpreter. Okay. And then we're going to load OpenCog, and we're going to load Atomy. So I'm going to type everything so that this is going to ensure that I'm not going too fast. All right. Okay, it's going to take maybe 1 minute because the first time it has to compile and it's a fresh image. Okay. Okay, now I can even show myself. So, okay. All right, so we're gonna enter all that in the atom space. So concept, it essentially means a set. So it's something that can have elements. So here we're gonna create the concept A, and we're gonna add some truth value to it. So here it means 0, 1. It has a strength of 0, 1, meaning the probability estimate of this concept being a representation of the universe is 0, 1 with a confidence 0.6. Okay, so now let's enter B. Let's enter C. So we're not going to provide a truth value to C, and that means that it has a default truth value. So the default truth value is actually complete ignorance. So if I enter this, it's going to be the same. So as you can see, the confidence here is 0. Meaning, I mean, the value here, it could be anything. It doesn't matter. It's just it's a flat distribution. Okay, here we have a subset. Right. So this means that the probability of B implies A is 0.8. Okay, and now we're going to do the same with, oh, well, maybe I made something wrong here. Anyway. Yeah, pardon me, it's A implies B. I think I. All right. Okay, so now we can see what we have so far in the atom space. All right, COG PRT atom space. Okay, as you can see, it didn't bother to redisplay ABC because they're already subgraphs of the subset links. Okay, so now that we have this, we're going to query this knowledge base. So let's first add some shortcuts. So define is just a well. So basically, so we are inside GUIDE. So it's a dialect of Lisp, and Lisp is basically the functions are in lowercase, while the atomies functions are in a camel case. That's a good way to make the distinction between just Lisp and atomies. All right. So these are variables. So they are atomic variables. And here we're going to define a shortcut for a type. So again, it's so this is atomy. So it means that it's the type concept in atomies. All right. Okay, and now we're going to write some queries. So let's start with something very simple. We want to query all concepts. So we're going to use get. So first we're going to use cog execute, which is basically the scheme primitive to run the atomy interpreter. Then we're going to use get to basically query the atom space. Here we have to construct type variable to type a variable. Okay. Then we use present, which is going to check whether whatever it comes across is going to be present. Well, the reason we have this thing is because we can have other kind of predicates. So that's why it's not how to say. That's why it's useful. But actually, what's going on here? Oh. All right, some little typo. All right. Whoop. What did I do? Oh, I forgot the get. Okay. Well, it's good that I make so many mistakes. That way, if someone else make mistakes, it will not get lost. However, I'm also going very slowly. So let's try that. Okay, it works. Okay. So yeah, I see that it's already Jesus. Time flies. So okay, I'm not going to type everything. If someone misses, it's okay. I mean, it's basically at this point, it's just for the show, for this part at least. So here, this query, what this query does is instead of fetching the concept, it's going to fetch all the elements of subsets. And if I want to fetch the subsets themselves, then I can use that. Okay, I'm gonna type this one because it's important. Here I'm using bind, which is like get, but it's also going to produce something, not just fetch something, but also produce whatever you give it in third argument. So here I'm going to have multiple variables, so I'm using variable list. And I'm going to put again my type variable x. So x is a concept. Okay. Y is also a concept. Okay, so that's for my variable declaration. Now I'm going to use present again, so I won't x, y, and a third argument. This is what's going to be produced. Of course, here everything that's going to be produced is already in the atom space. Okay, so we have all subsets. But in the next one, we're going to produce something new. Okay, I'm not going to type this one because, I mean, there's nothing new in it. But the result's going to be new. That is, I mean, it's basically a one-step transitive closure. So if we have X is a subset of Y and Y is a subset of X, then we can infer that X is a subset of Z. So okay, let's do it. So it's able to generate that. So now if I well, okay, let's do card print atom space. We're going to see a lot of stuff now, because the thing is that all these queries now they are in the atom space. Okay, if we don't want them in the atom space, we can actually create another atom space and put them there in the first place. But that's not what we've done. Here if we look for it, we should be able to find, yes, it is here. A is a subset of C. All right, the newly inferred knowledge. However, this thing is just, it's completely crisp. It didn't use some truth value on the subsets, and it didn't produce a truth value. And what PLN is going to do is basically that, but at the step where we have to rewrite the term, it's going to invoke a formula, and this formula is going to calculate the truth value. All right, so we're going to move to PLN, which is going to do just that. So let's load PLN. Okay. All right. So now we are going to load an empty rule base. I mean, because there are different layers of PLN, and we're going to start from empty. And we're going to add just the rules that we need, which are deduction and modus ponens. Okay. PLN actually lives in another atom space that can be printed with PLN PRT atom space. Okay, so there's a lot of stuff here. That's because it has loaded all the available rules, or most of them. However, we have only attached 2 rules, and they can be displayed with the PLN rules command. We can also show their weights with PLN weighted rules. As you can notice here, the weight is not a single value, it's a truth value. That's very important because it allows not just to give a priority to rules, but also to balance exploitation and exploration. So here, everything is flat. So basically, what it means is that we have no idea what is better than the other. Okay. If we had some idea, then we could say, oh well, I have some little ideas that modus ponens is maybe it's a little bit better than a deduction rule. But because we have some low confidence, there's going to be a lot of exploration still going on with that. And if we want less exploration, well, then we increase the confidence and so on. All right, so now let's try to use these rules. Okay, we're going to use the same thing we had before, but let's just remove a lot of junk in the atom state that we have accumulated. So that's just what we had before. If someone cannot copy paste and wants to follow along, this someone's going to have to retype everything, and I apologize for that. I don't know if I have to wait this someone or if I should move on. let me just wait a little bit. So this is this thing. While I'm waiting, any question?
I think somebody on the YouTube chat was having a little bit of issues working with Emacs. So whether you could quickly just like show how to do it differently for them, perhaps.
Well, yeah, I mean, for someone who's not used to Emacs, is a little bit of a problem. Yeah, I mean, I would. So okay, if someone is starting from scratch, like someone has tried Emacs and wasn't able to use it. Okay. Before I say that, just let me, I mean, just to give us a chance to Emacs, in order to change the window, it's Control X O. Okay, Control X O. What else should I say? In order to bring the shell, it would be Alt X, and then you can type shell. Okay. In order to split the screen in two, you do Control X and 3. Okay. And if you want to remove the splitting, you do Control X and 0. Sorry, Control X and 0. Here I'm gonna split again. Control X O to move to this screen, to this window buffer, we say in Emacs. Control X to come back. Control X O to come back, I want to say. I'm going to select the shell with Control X B, then I type shell, and I'm there. But if someone wants to start from scratch, at this point, it's still possible. All that this someone has to do is re-import everything, OpenCog. I think actually only that's going to be necessary. I think that's going to be enough. Use modules, OpenCog PLN, then load. So let me just show as much as I can. Right, so here I'm showing everything. All right, so import OpenCog and PLN, load the anti-rule base, add these two rules. Well, this is not necessary, and then can bring the knowledge base, which that's all of it, right? Okay. By now, do you think I should move on, or I should, or?
Yeah, I think if there are no other questions, then we can just move on.
Okay, great. Okay, so before I run PLN, I'm going to set some parameter. This is going to allow to, so the name of the parameter is complexity penalty. I set it to 10, and what that means is that PLN is going to focus on simpler inference trees first. I do that because otherwise I might run into the risk of having PLN just evolve bigger and bigger inference trees in a runaway fashion, and it might miss the simple inference that we want here. Okay, so interestingly enough, the parameter actually exists inside the atom space, the PLN atom space. And so now, okay, let me type it. So PLN BC stands for backward chainer. What that means is that we're going to start from a theorem and we're going to go backward. We're going to apply the rules backward until we reach the knowledge base. So, okay, let's try. Okay, it seems to work. So it has applied. Here's just one rule. It's a deduction. Okay, to see what's going on behind the surface, we can enable the logger. So we're going to set the level of the rule engine to debug, and we're going to have it display things right in front of our eyes. Okay, and now we're going to rerun the same thing. So before that, I'm going to have to reset the truth value of C, the target. Well, sorry, just a second. Oui, non, là, je peux pas, là, je suis... Ben oui, mais attends. Ouais. Ok. What? Ben, si, il y a une caméra. Mais elle te voit pas, t'inquiète pas. Alors. Okay, so where was I? Yeah. So, okay, we are resetting the truth value of C. Okay, and we're going to rerun. Oh, what is that? Yeah, so we were here, right? So we're going to rerun the backward chainer on C. And it's going to display a lot of stuff. So we're going to limit the number of iterations to 10. And okay. So obviously I can't explain much of what's going on here, but there's something I'd like to show you. And these are the inference trees. So this one is actually already more complicated than we need. The one that gave us the answer, well, it is this one. Wait, I've lost track of. Yeah, no, actually, it is more complicated than that. It's going to be this one. Yeah, and you can see that the results here. Well, that's what we were looking for. Oh, actually, well, okay, something going on here. What? Sorry, a little bit of disturbance. Okay, I could lock myself again, so should be okay. All right. Okay, well, there's a little bit of there's something there's a little bit of fuckery here. I don't know what that is. I guess that there's another inference tree that is producing another value. All right, so that's where, I mean, dealing with uncertainty is very tricky, because like you obviously have many more paths to reach the same conclusion. Yeah, so this is something that is often a well, rather tricky aspect to deal with. Okay, but let's move on for now. So, okay, now we're gonna, okay, we have 15 minutes left. Do you want me to keep going with PLN, or do you want me to move on to the pattern miner? Maybe I can show this thing, but very quickly, right? So I'm just gonna.
One person says pattern miner.
Right. Okay. Okay. So I'm not gonna type that. So I mean, it is just to show that we can also do reasoning based on evidence, based on direct evidence. I mean, so it's kind of a idiotic example about the probability of growing a beard during a pandemic based on a very small sample of people. The interesting thing here is that we have these kind of rules that, this one is called subset direct introduction, and direct means that it's basically direct evidence. So we're going to look at, so the direct evidence are these members of, okay, this instance of individual happened to go through a pandemic, okay? This instance of individual happened to have a beard, okay? And so based on that, is going to be able to estimate the truth value of such a, just a second, sorry. Okay. Okay. And so, okay, we're gonna disable the log because it's gonna be overwhelming. And so now we can, based on direct evidence, infer the probability of growing a beard during a pandemic. Okay. So, well, based on the evidence, it is the correct probability. Okay, but what about, for instance, growing a beard during a pandemic? Why being a man? Okay, it should be much larger. Okay, so let's run PLN over that. So it's not able to infer anything, and the reason is because it doesn't know how to deal with that. I mean, there are no rules to deal with this conjunction of man and pandemic. So for that, we're going to need to okay. And for that, we're going to need to add some more rules. Okay. And then we can, so okay, let me just go over these rules rapidly. So here we have this rule, conjunction direct introduction, that allows us to basically, given two concepts where we have direct knowledge about them, how to deal about the conjunction of that. Here we have something that allows to infer, to evaluate the truth value of a concept, well, given direct evidence, and here we need this thing because, well, I mean, I was too quick to show that, but basically there are some things that we don't know directly, so and so there's a little bit of inference to be done in order to extract this direct knowledge. And now that we have this, oh, it doesn't work. I mean, maybe we didn't put enough iterations, so let's just, I'm going to put 1,000 to be really sure. It's taking a little bit of time, but should be over soon. Right, and so it found the correct answer. Because, well, based on the available evidence, well, the probability of growing a beard for a man being in a pandemic is 1. Right, okay. So let's move on to the pattern miner. So let's clear the atom space. Yeah, I've got like 10 minutes left, so I guess I'm just gonna copy paste until the end. All right, so this is basically what was in the presentation. So A is a subset of B, which is a subset of C, which is a subset of D, etc. So just want to see if we can find what we're supposed to find. What's wrong here? Oh yeah, I forgot this step. I didn't load the pattern miner. Okay, let's try again. Okay, so it has found a bunch of stuff. Yeah, and the most surprising one is the one that we're looking for. So it's basically A is a subset of something, and this something is the subset of E. I mean, so it's basically here. Okay, that's a little bit more complicated than what was in the presentation, and that's because here we have actually the measure of surprisingness of that pattern, which is going to be this value here. It's a single value. That's why the confidence is at 1. And you can see that this pattern is read by a lambda link. So lambda link is I mean, it means the same as in lambda calculus, but basically it is a function that if I give this function to atomies, to the pattern matcher, it's going to be turned into a query. So basically, I can turn this pattern into a query, which can be very convenient to understand. Well, why this pattern is surprising? What are the data behind this pattern? Okay. Okay. And here we have another example. So let me clear the atom space again. So it's also a toy example, but I mean, I can only present toy examples because otherwise computation would go would take too long. I mean, we have experimented the pattern miner on some interesting data sets, sumo ontology, bio atom space, biologics data set, which include millions of atoms, and of course it works, but I mean it takes a long time. So for a live tutorial like that, I can only show a moderately simple data set. So KB, here it is. Well, it's a goofy data set about people drinking soda and stuff like that, and the pattern that we want to find is going to be this one if it works. Let's see. And it doesn't. Okay, what's wrong? Why does it work? Yeah, I tested everything in this tutorial except this last one. So
I think it's an extra bracket at the end of that line.
that shouldn't be the reason. Let's see, but I mean, invalid handle. That's odd. I think it has to do with that, but it worked before.
I was
Oh well.
I was able to execute just by deleting the last brackets.
What did you do?
Just deleted the ending bracket that was not necessary. That one is not necessary, and just copy paste that. It should, I guess, it should work. It works here.
Yeah, I might have included something else as well. Maybe the. Oh, that's odd. I did a clean. I mean clear. And maybe you didn't do that. You know, I did that clear. And I wonder if there was maybe there was something useful,
Right?
And it was cleared or something like that.
Maybe.
Anyways, I mean, I don't know if there's a point debugging that right now. I think it's already a pretty good overview of what can be done. And we have only 2 minutes left. So it's better to use that as maybe questions or
Oh, yes. Okay. For some reason, I thought it went another half hour, but you're right.
Oh yeah, maybe. Oh, I think you're right.
No, but either way, I mean, there's nothing after this. So if people have questions, we can take them until the end. So, but it does end at 2 Eastern time.
Yeah. I mean, I had. I mean, well, anyways, I mean, I think it's. I mean, it can be the end of the tutorial, and yeah. Any question or?
Predrag, I probably strong would say, says extra bracket, delete ending bracket.
Yeah, that was regarding the last statement, but it's
the last statement. Okay.
Yeah, I mean, it works here. But now that you mentioned my name, I have one question regarding this Lambda link. What kind of, because I'm very new to COC, what kind of functional language expressions or constructs you can basically have within the atom space, and can you somehow describe types?
So yeah. So we have everything, but I mean, I want to say almost the most essential. We don't have currying. We could have it. I mean, it's just we just need to introduce this link, this operator, and we would have currying, and then we would have, I think, everything. I mean, well, the type system is not the most elegant one you can get, but I mean, we could turn it into an elegant type system. Other than that, I think we have it should be basically lambda calculus plus plus or something.
And if you, I mean, can you somehow compare it to some existing popular functional programming language? Is that does that make sense at all? I mean,
well, so okay, yeah, I think I oversaw something. We don't have either, for instance. I mean, the notion of purity is very sketchy, and it's not basically. We don't have monad or things like that. Nothing is guaranteed to be pure. So I think we need to have a way to enforce purity. I think it can be done in the, in the type system, or maybe in the hierarchy of atom types. We need to add currying. And if we have these, I think we have, it's not going to be Haskell because the syntax is rather different, but beyond that, let's say it's going to be, it could be Haskell with a bad syntax or something like that. And
so
with a limited type system.
I see. That's useful because now people who have this kind of background can easier can get into the it's easier.
I think these functional additions are extremely useful. It's not just, the purity is extremely useful when you want to memorize anything, memorize reasoning, memorize computing, etc. So I think it's very important, and I think it's gonna get. It's gonna be added whenever the need is gonna be pressing enough. It's gonna be added, I suppose. Either it's gonna be in this version of the atom space or in the next one, but.
So when you say memorization, is that just for practical scalability purposes, or sometimes that can be something which has some theoretical consequences, using memorization or not using memorization?
If practice is taken in a broad sense, if efficiency is, I think it's only for efficiency. I don't see another. I think I see what you mean, in the sense that, right? If you reason about a part of your environment that is just completely static, you're going to be able to enable some inferences that you won't be able to do if it's dynamic. So I can see that.
Okay, right.
Добре, чакайте.
Memoization, that affects what size patterns you can actually learn within a certain amount of time. So in a sense, that's scalability, but it affects what the learning can do. So in that sense, it's not like the system will come to the same conclusion, but just faster. I think it will find different things in a real context.
Right. I understand what you mean. So yeah, it has some practical consequences. Yeah.
I mean, it's changing the distribution. Yeah, it's changing the distribution of the learnabilities of different possible patterns, I think.
Right. Yeah, because of because probably the most of the applications in the real world will be complex enough, so this could impact in some very important ways the operation of the system. I see.
Yeah, because the patterns where memoization can help a lot ultimately they're gonna more often be parts of larger patterns. So it should affect the distribution of which patterns are more easily learnable by the system within a certain amount of time. I mean, if we tried to cash that out in a mathematical way, which we haven't done.
No, but I mean, the memorization is important, interesting to me because I saw some of those prologue systems where they, I mean, I don't know if tabling is something related to this, but it has some consequences, but I'm not so sure where this is, but it seems similar in some ways. Because there are some things here from what I can see in this scheme code and also in background system that reminds me about the prologue systems. Of course, there are some prologue systems.
Yeah, there's some similarity there. I mean, of course, I'd say, as Linus Vepstas has pointed out, there's a bunch of similarities between what we do in OpenCog with pattern matching and probably data log more than straightforward
pure version.
It's a bit like probabilistic data log in a way, except I mean the underlying search algorithms are not the same, but still the implications of memoization for what is more easily provable or learnable may be similar to what you're thinking of. Yeah.
Thanks, guys. Maybe somebody else has some other question. I don't want to bug everybody.
Oh, you're not bugging us. You can say whatever you want, of course.
Okay, sure. Great. I mean, it's excellent that this is virtual. Everybody can participate.
That's true. That's true. It's open for all. Let's see. Any questions? Check the chats.
Yeah, this
Go ahead. Okay, there are no further questions anymore. Ben, would you like to give a last word, perhaps?
this is not a question, but it's a comment on something that I didn't hear all of Nil's tutorial, but I think one additional point that's interesting to reflect on is the interoperation between pattern mining, which Nil has been working on and showing off, and then probabilistic inference on the one hand, and evolutionary learning on the other hand, both of which also exist in OpenCog, because I mean, as Noah's already done some examples of, sometimes the best way to do pattern mining is to hybridize it with inference, which is sort of a unique point you get from doing pattern mining in something like OpenCog. So like if you were I mean, as a simple example, suppose you were mining an Atom space full of people, data about people and their jobs, and you wanted to learn, how many people who hate their jobs are also depressed, right? So I mean, one thing you can do is just have the pattern miner scan through the Atom space, and for each person it visits, check how many people hate their job and are depressed according to the knowledge explicitly in the Atom space. Another thing you could do is go through and for each person in the Atom space, do a little bit of reasoning to say, well, do I have a reason to believe they hate their job? Do I have a reason to believe they're depressed? And maybe for some person you find information that they're saying they hate all the people at their job, or you find data about their happiness level throughout the day, and you find they were happier at home than on the job or something. So you have indirect evidence that they hate their job. And so then one can use the pattern miner just to look for patterns that are explicitly there in the Atom space, or you can use the pattern miner to find patterns that appear in the Atom space when you apply a bit of reasoning at the point where you're trying to do the pattern match. And this is the sort of thing we want to be able to implement in sort of a slicker way in the future, using a sort of an Atomies 2.0 language, because it has to do with how static pattern matching interoperates with these dynamic cognitive operations. And it's also like a simple type of cognitive synergy between pattern mining and inference. And then the other interesting intersection was to do with the evolutionary learning. So we have Moses, which is a probabilistic evolutionary program learning algorithm sort of associated with OpenCog, but right now it's been running outside of the Atom space. When you use Moses to learn programs based on a certain fitness function, those programs can then be imported into the Atom space for follow-on reasoning. But there's a project that's been going on for a while called Atom Space Moses to re-implement the Atom space, to re-implement the Moses automated programming learning framework inside Atom space entirely. And when that's done, then it could be used, among other things, together with pattern miner. So Moses it's doing evolutionary rather than non-greedy search. So you could use Moses as a control mechanism for pattern miner, which is not just doing the incremental greedy pattern mining that the pattern miner is doing, but is using evolutionary learning and probabilistic modeling of the evolving population to suggest new patterns. And I think that's probably ultimately what we need. Like the purely greedy pattern mining, which is done in the current pattern miner, that's great. I mean, it doesn't require any background knowledge or any special assumptions. You just go and find small combinations, slightly bigger combinations, and so forth. On the other hand, you'll never build up to really big and complex patterns that way, right? You'll get a bunch of simple patterns. Then evolutionary learning, if you have the right kind of structures in the Atom space and or the right kind of prior knowledge, you could use that to discover much larger, more complex patterns, sometimes using the simpler patterns gotten through the greedy pattern mining process as inputs. So I think the current pattern miner can be quite useful right now in a whole bunch of different domains, just on its own, but sort of moving from narrow AI for pattern mining on graph and hypergraph knowledge stores toward AGI, the use of the pattern miner will be substantially about its integration with reasoning and evolutionary learning. which is all stuff Nil and I have been working on slowly in the background, whereas in this tutorial, the focus was on the stuff that already works quite well.
One of the things that inspired me a lot of this, I mean, recently was the open-ended evolution. So maybe that's like after you have this kind of greedy approach to finding things, maybe there is like some kind of approach which might explore and then pick some.
Yeah, well, there's one of the crazier ideas I had, which we haven't been able to explore yet, is in the 90s, I was really into an AI approach called algorithmic chemistry, which was developed by a guy named Walter Fontana. And there's related stuff being done now, like Marius Buliga's Chem Lambda system, which is quite cool. The idea there, you're getting beyond just simulate evolution to simulate chemistry. So you have like a little codelet acts on another codelet and produces another codelet, or maybe this codelet somehow catalyzes the combination of these codelets to produce a third codelet, right? And we were doing this in the 90s with little Lisp programs, actually, even as bad as computers were then. You can do much more interestingly with that now. Now that, I mean, that led to interesting theory stuff on, you can find like autocatalytic sets of programs and so forth, which all produce each other, which is quite evocative of biological systems, right? On the other hand, what I'd thought was, if you did this sort of algorithmic chemistry with codelets that live inside OpenCog atom space, then you can try to boost the evolution by doing pattern mining and reasoning. Find like, well, when I combine codelets of this type, it often gives me a codelet of that type, right? When the codelet of this type catalyzes this type of code reaction, that's often useful for this goal. So then you're using the pattern mining and associated reasoning and evolution to sort of accelerate the algorithmic chemical reactions. So that's my best thought about how to get like radical computational creativity going, right? Because I mean, that's these sort of self-organizing autocatalytic evolving networks are how, at a certain level, that's how biology created all these weird forms like us, right? But then
life itself,
Life Itself, which is a book by Robert Rosen presenting similar ideas, actually. Yeah, the thing is, the current OpenCog framework would make that a bit awkward and inefficient, although you could certainly do it. So we're sort of wanting to come up with a mathematically similar infrastructure that runs faster for playing around with these things. Although, to be fair, doing it in OpenCog now would be faster than what I did in the 90s, which still had some interesting results. But what you see, like what OpenAI is doing, largely they're taking algorithms that in concept have been known quite a long time, and they're just applying them on massive amounts of data and massive amounts of machines. So there's a lot of things you can do that with besides deep neural nets, like algorithmic chemistry as one example, or very many deep things in artificial life. We just don't know which of these things in artificial life or algorithmic chemistry didn't work because the scale was wrong, right?
Without compute, yeah. Yeah, I mean, it's interesting. One also interesting idea that I recently learned about is the idea about, I think that's coming from the neuroscience research. I think that the person is called, I guess you heard about him, Carl Friston, and he is basically talking about what makes something alive. What is this?
Well,
Where is this barrier? what is
So-
outside of this thing, right?
I mean, so Carl Friston, yeah, he's a neuroscientist, and I can't comment on his neuroscience. I would say his attempt to formulate an entropy-based principle as the basis of intelligence seemed to have many, many holes in it, right? Because I mean, if you look at, I mean, he looks at minimizing entropy as the basis of perception, but when you look at what he's doing, pretty much he's just saying the model in the mind has to agree with the world. So it's really just minimizing KL divergence, which is not a new idea. And when I look at what he says about entropy minimization as a way to choose actions, he's sort of just saying that we need a model of what our actions will do that agrees with reality, which is just mapping action into perception. So I sort of felt like the philosophy is there, but the math
It's too simplified. It's too simplified, man.
Quite there. Yeah. So I mean that's what I mean, that's part of what I was thinking when I was looking at, okay, if you have maximum entropy principles, then you have Janes with the maximum caliber principle, which is like maximum entropy for temporal systems, right? So you have it's like maximum path entropy. So if you have a system evolving from one point to another, given some observations of what the system did, what's the most probable hypothesis about how the system evolved? It's the one that maximizes the path entropy, the entropy of the possible paths the system could take, which is what he calls the caliber. Then you can look at like algorithmic caliber and just algorithmic information and see. So the notion of that given a bunch of observations of a system evolving over time, the most likely hypothesis for what the system is actually doing is that it's enacting the program with the maximum algorithmic caliber over that interval, and that ties in with like algorithmic Markov condition and like algorithmic Markov nets and so forth. So it seemed like there's a theory in the direction that Friston is pointing, but it's not the exact theory that he's pointing at. Now, from a neuroscience point of view, which is his background, who knows how much difference all these mathematical niceties make? I get a feeling they do make a difference if you really boil down to like quantum chemistry in the brain, which is where all the neuroscience magic is happening. There's probably some quantum information theory ultimately that you need there, for which it may actually make a difference to get the math of the information theory right. But we're not quite there yet. So all that's super interesting. On the other hand, I'm hoping I can set it aside to build AGI systems, right? Because that's
something more concrete.
That's all very hard on its own.
Right.
But yeah, there's that. I mean, how to measure information, which is what Friston is pointing at, though I don't like his answers. But how to measure information is certainly important for AGI also, right? Because the system needs to create intrinsic reward criteria for the things that it's learning, and like if for the patterns that it's recognizing. And this gets back to the pattern miner in a way, because you can use the pattern miner to look for frequent patterns, or you can use it to look for surprising patterns or interesting patterns. And there you have the question like, what is an interesting pattern, right? Is it one with a high like endpoint mutual information, like interaction information? Is it one with a high interaction information conditional on your knowledge? I mean, in a way, if you could solve the problem of correctly formulating what's an interesting pattern, that plus large scale computing brings you a long way to creating an AGI, right? Like I thought this in automated theorem proving, for example, one of the shortcomings of the field is you don't have enough theorems to train your automated theorem prover. Like in natural language, you have a lot of sentences, but math, there's only that many proofs that have been formalized, and they're quite complex. So you want to train a machine learning algorithm on how to prove theorems by using existing proofs as examples. The number of existing proofs is arguably too small relative to the complexity of what the proofs are doing. So the solution will be to automatically generate a humongous number of new proofs. On the other hand, just randomly generating meaningless math theorems and then proving them with an automated theorem prover is probably not what you want to do. But if you could randomly generate billions of interesting theorems by the right interesting criterion, point your automated theorem prover at them, then you could generate a corpus of interesting math proofs like 1 billion times bigger than what we have now. Then you could train your machine learning theorem prover on it. And so and there's obvious recursions and virtuous cycles here, right? Because the better your theorem prover gets based on the machine learning learned from the corpus, the more easily you can prove more interesting theorems. But we don't yet have a really good formulation of what is an interesting math theorem, right? Because in some cases, one guy's interesting theorem is another guy's boring tautology. Like at one point in my life, I thought the quadratic formula was really interesting. I was like 7 years old or something, right? Or then like the generalized, like Frobenius theorem, that the only division algebras over the reals are real complex, quaternion, octonion. I'm still not sure if that's interesting or just trivial, right? So there's as a mathematician, that everything that's already understood is trivial and not interesting, right? So there's
for me, I had sorry for interrupting, but regarding this interestingness, there is one project called Dreamcoder from MIT, Dreamcoder. Basically, they are trying to synthesize code, and their architecture comprised of two important stages, like baking and dreaming cycle. And basically, the dreaming cycle includes some of the neuro models like deep learning, and the baking cycle is more enumeration. But there is one possible criteria for interesting, basically subprograms, like subtheorems, like, and that's if you can refactor, for example, translated to domain of theorem proving or discovery in mathematics. If you can, for example, refactor some of your work in certain ways, so to use some kind of like a stepping stones. Maybe these are important theorems that then you can use to drive this process to find additional.
But this, it sort of recurses, right? You say an interesting theorem is one that's a lemma to a lot of interesting theorems.
Yes.
It can't be the whole answer, though, right? Because where does the induction bottom out, man?
Okay, but can you say? I mean, maybe it doesn't make sense. But for example, something which can simplify a lot of theorems, which might not be interesting in any way. Maybe that's valuable and interesting on its own.
Well, I think we're getting, the natural language terms here are a problem, right? Because interesting in this sense doesn't mean conceptually interesting. Like the commutative law of addition is not really very interesting, but it certainly is extremely useful, and it's a subcase of it's a lemma or whatever for a lot of different theorems. And I guess if you're in piano arithmetic, then getting the commutative law, it is kind of interesting. It's a lot of S's you have to shuffle around to get to the commutative law, right? So that's what you said might be correct.
It's compression.
Not
just
clear because the space of all random theorems is weird, and there might be some completely crappy. It might be that any theorem at all can be a lemma for a whole bunch of stupid random theorems that you don't care about. So it's it's you come up against like everything that we're interested in, or that any intelligence with any finite resources, intelligence in the real world could ever be interested in, is like in a teeny tiny little corner of the space of all possible mathematical structures, right? So like we're interested in things that can be composed hierarchically because our physics works that way and our brains work that way, but yet almost all proofs that you sample from random proof space have none of that, right? So
yeah, but if you have system which works pretty good for this completely chaotic something non-human relevant parts of mathematics, maybe it will be super easy then to just pick.
No, that may be sufficient, but it may not be necessary, and it may not be possible to find those things. Right?
Okay.
But I mean, in reality, what you can do, you can build up a certain corpus of theorems, and you can see, like, if a certain lemma is useful for simplifying the proofs of a lot of them, then maybe it's good. And then there's that sort of an interesting empirical / theoretical question, right? Because you could, like, we could look right now. I mean, we could take a whole bunch of genuine proofs, and then we could take proofs of theorems that humans care about, and we could generate like an equal number of true theorems that are just synthesized by like forward chaining from axioms. Then you could pattern mine and see which patterns occur more often overall, or which patterns occur more often in the human math versus the random math. And then you would see, we could actually see which of these patterns were more useful as lemmas for proving more human math or more random math or whatever, right? So I mean, this it is actually tractable to experiment with now. One of the questions is how similar are the answers for math theorem proving versus the answers to common sense reasoning? Because my son is doing his PhD in automated theorem proving, I've been talking a bunch to folks in the automated theorem proving community, and at an abstract level, they're wrestling with the same issues that Nil and I and Matt and so on are wrestling with PLN all the time. But the statistics of the theorem and proof space are different, right? Like in math, you have very few axioms and very long proofs. In common sense reasoning, you have very many axioms and very short proofs. And it's
shallow proof.
And so it's not quite clear which conclusions are generic across those two cases, and which conclusions are only good for math or only good for common sense. And then when you talk about a non-human AGI, maybe that dichotomy is less meaningful, and they're reasoning in some way that's like halfway between what we think of as math and what we think of as common sense. It's not clear how fundamental that distinction is.
No, I think maybe the path towards separating or selecting is just create an AGI system, some kind of artificial system, which actually is doing autonomously physics research or any kind of science research, and it will basically try itself.
Yeah. I mean, that in biology, there are areas where you can do that now because they're in theory. I mean, there's automated lab equipment. Like you can do microbiology experiments purely with robotized lab equipment. So like an AI can crunch biology data, design a new experiment in the Petri dish, run it, take images, analyze the images, design new experiments. And this is not being done at large scale anywhere, but you certainly could. I think it would be really cool to do that in bubble chambers or something, because you would think the AGI might come with a whole different descriptive language for what's happening in the bubble chamber, because our words and our math for describing these things obviously are quite limited, and most events in a bubble chamber are thrown out as noise because they
what is bubble chamber?
Basically a chamber of gas that you're shooting elementary particles through to see the collisions of particles and the scatterings. And most events there are being thrown out as noise because they don't meet the criteria for an event of identifying a particle, right? But you wonder if you're pattern mining across all these events, like maybe there are actually interesting.
The noise, yeah, maybe this noise contains some information, but it's like
yeah,
alien.
because you know there's quantum non-locality, and I mean there's quantum coherence in unexpected aspects there, right? So again, this is really big data, and we can't apply the OpenCog pattern miner to it in its current form. You can do something similar with different software, or we can wait until we have a massively faster OpenCog. But overall, setting aside AGI and OpenCog, there's no one even applying like the most advanced large-scale machine learning to like unsupervised pattern mining in data from particle accelerators and bubble chambers and so forth, because we're much more interested as a society in analyzing data on who will buy which useless garbage.
Crazy.
There's a question on YouTube whether pattern mining beats neural networks in terms of answering why did you do this. I'd say, I mean, neural networks is a very big field, but if we're looking at the types of neural networks in common use now, I would say neither pattern mining nor any of these commonly used neural networks is much good at assessing causality. But our PLN logic inference system, which is designed to work with pattern mining, has some causal inference built in. I mean, as such, as Neil presented it, the pattern miner is just looking at what patterns are there in the data without trying to disambiguate correlation from causation. In that way, it's similar to XGBoost or a neural network or whatever. But those patterns could be fed into an algorithm doing causal reasoning or an algorithm trying to extract causality from directed acyclic graphs or something. But so I would say pattern mining does better than current neural networks at generating raw materials to feed into a causal inference system, because it's very hard to extract information from within most current neural net architectures to feed into your causal inference engine. Whereas pattern miner, you can look at the details of what it extracted. It's transparent and explainable, which means you can feed it into a causal inference engine. Someone asked, Anatoly asked, can you hard code? Of course it could, but it would be even slower, right?
What's the question? Lambda link, URE?
Question was, could the hard-coded lambda link be implemented on top of the URE?
Well, maybe in principle, but in practice, the other way around.
Yeah. Oh no, Anatoly. That question is from Anatoly, who knows the system already. So, I mean, mathematically, you could do it that way. It would just be unnecessarily inefficient in the current implementation. I mean, there's no reason you couldn't.
Yeah, makes sense. Thank you.
Yeah, I mean, well, it depends on the other primitives, but yeah.
Well, I mean, yeah, sure. I mean, if you have basic predicate logic, you could build lambda in terms of a standard first order predicate logic or something. Right?
Yeah, I just noticed that in Prolog it's the other way around. So in Prolog they implement lambda calculus on top of pure
I mean,
logic.
Prolog sucks even worse than the current atom space. So, and in many ways, I actually, yeah, this gets back to sort of Alexei's and my OpenCog 2.0 thinking, right? Like you really, I'm not sure you want either of those. You want logic or lambda. You want first order Praga logic or lambda calculus to be able to exist on the same atom space without having to shoehorn either one into the other one. But because either way is either Prolog way or the current atom space way is unacceptably slow for AGI, I think.
Yeah.
Ibby is asking if OpenCog can represent truth with a capital T.
Yeah,
Matt, do you have any comments on the absolute and eternal truth in OpenCog?
Can it represent Ben?
Well, yeah. I mean, well, I would say in seriousness, there's a lot of theories of truth out there in logic, right? And from a logic view, truth is about model theory, right? It's about setting up correspondences between your logic and your model. And what we're aiming for with scaled up OpenCog as we work on revising the system is actually a system that can concurrently easily represent multiple different logics and models and multiple mappings between them. So that's more like the postmodernist version of truth. We want various truth theories to be easy for the system to experiment with. But I mean, yeah, these philosophy questions we could interpret in a lot of different ways.
That brings up a whole. I mean,
yeah,
you
I mean,
have
the
truth.
Truth in formal logic has a certain flavor and history behind it, which doesn't capture all natural language interpretations of the concept of truth. Right?
Yeah, I mean, even like the most popular theory of induction, so Solomon induction. I mean, it is it's still arbitrary in a sense. We trust it because it works and it feels right. But I want to say, even when truth, even when we're talking about truth as it relates to reality, it's just not clear what it is. So.
No, I mean, in practice, what we're thinking about is a system that can create models that are less erroneous than its previous models, right? And that's you are improving your understanding and reducing your stupidity. And I mean, like Charles Peirce, the philosopher, viewed that as something that was ultimately converging toward truth, even if you never actually get there. But we do, in a very nitty-gritty sense. I mean, in PLN logic, which is one of the key inference ingredients, probabilistic logic networks that we've been playing with in OpenCog, you label nodes and links representing terms or predicates with truth values, which can be single numbers or first or second order probability distributions. But we intentionally don't assume that you have a single consistent probability distribution over all the nodes and links in the atom space. And this is an important thing that PLN within OpenCog shares with Pei Wang's NARS, non-axiomatic reasoning system, which there's a tutorial on at this conference also. I mean, NARS doesn't use probabilistic semantics for the uncertain truth values in its knowledge graph, but NARS, with its non-probabilistic uncertain semantics, has in common with PLN that has its probabilistic uncertain semantics. I mean, it has in common, you don't try to have an overall consistent probability model over all your knowledge. And there's a couple reasons for that. One is, philosophically, we both sort of feel that's not how human minds work. And the other reason is it's quite inefficient every time you have a new bit coming into your system to have to update all of your knowledge based on that one bit of information. So as well as being conceptually questionable, having a consistent probability distribution over all your knowledge gets less and less efficient. And especially if you start to think about a distributed system or like a decentralized system implemented on something like SingularityNET, you just can't do all that updating, and that you get pushed toward what logicians would call a paraconsistent logic, where you can have some types of inconsistency, but that if a small inconsistency doesn't necessarily pollute the whole knowledge base and make everything inconsistent. And that's a sort of reason why we humans can think like, I love my girlfriend, I don't love my girlfriend, but we don't from this conclusion logically derive that like I will drown if I jump in the water, I won't drown if I jump in the water. Whereas a standard predicate or proposition logic system, if you have one contradiction, you can derive everything, right? Humans have some paraconsistent reasoning that isn't like that. What's interesting, as I mentioned in the previous tutorial or workshop rather, I think gradual typing on the programming language side is sort of is isomorphic to paraconsistent logic on the logic side. So if you create an atom space that supports multiple different type systems for different collections of nodes and links, and which lets you have nodes and links without their type specified initially, and then determines what type they have only when you need to for doing something with them, that sort of gradual typing system actually corresponds to a paraconsistent logical reasoning system, which I think probably is the right way to go for general intelligence. But again, that's a research hypothesis yet to be validated.
I have a question. There seems to be very good progress with PLN recently, and what I wonder is, what are your plans for causal inference in the future? Do you plan to integrate this component into PLN itself, or will this be a separate module or something like that?
So we're experimenting with causal inference now in the biology context, for like trying to find out which, I mean, that's pretty simple. Like you want to cure a disease, you want to figure out which genetic variations, say, are actually causal for this drug curing someone of cancer or COVID, rather than just cofactors or correlation or something. So we're experimenting with that now within OpenCog, and it's, I mean, OpenCog acting on the outputs of machine learning algorithms along with biology background knowledge and so forth. And that's a case where there's, for many diseases and drugs, like there's ground truth knowledge about which things are causal and which ones aren't, that you can use to validate your methods. Like for cancers, there's some. For COVID or aging, there isn't as much. So I'd say at the moment we're in an exploratory phase with that. Like we had a bunch of math written down about causal inference in PLN, and we've been doing other causal inference stuff outside of OpenCog on biology data, just with information theory analysis. So now we're trying to see what will work in that domain. And based on what works or doesn't, we'll make a detailed path forward. But my guess is there's going to be a couple aspects to it. So I mean, one aspect is you have causal implication link in PLN, and then you can do inferences on causal implication link. So like A causes B, B causes C, in what cases and to what extent does A cause C, and so forth. And then you have interesting relations between intentional logic and causal logic, right? So there's interesting stuff there. On the other hand, there's probably also some sort of explicit search for DAGs that are causal DAGs embodying some approximation of an algorithmic Markov condition. And that may be like a DAG model structure search type thing rather than a forward or backward chaining inference type thing. Like once you've done inference to learn a bunch of data, that data is all a tangled cross-connected graph with many, many links, right? So then in a way, it's like finding the maximum information partially spanning algorithmic Markov DAG, right? Like you're trying to find a causal model that summarizes this cross-connected graph, and maybe that's a separate process than forward or backward chaining, but of course they could both help each other. So that's because this gets back to pattern mining is greedy, right? And in a sense, forward and backward chaining inference are greedy also. They're going step by step, although we can try to guide them with machine learning models, trying to have prior proofs, which are a little less greedy. But you could, for example, use evolutionary learning to try to evolve causal DAGs, right? And then that's not greedy in the same sense, because you're crossing over one okay causal DAG with another okay causal DAG to find maybe a better one, like in the genetic operator sense, and you can build a probabilistic model of the structure of the causal DAGs, like in Bayesian optimization algorithm applied to program evolution, right? Where you say we have these okay causal DAGs, these bad ones. So what's a probabilistic model of the structure of the good causal DAGs versus the bad causal DAGs? And then that's like basically atom space Moses used to evolve causal DAGs, where the fitness of a causal DAG has to be figured out by PLN inference against the atom space. And I mean, ultimately, I think that's where we have to go. I hope we don't have to go there to solve the bioinformatics problems that we're facing right now, because the ultimate thing I just described is quite difficult, right? I mean, how are you doing causal inference in NARS now, actually?
Currently, it's a quite simple approach where we essentially apply subcoding. So we just have a implication relationship, which might be similar to what you use. And from there, so when a core enters the system, it simply tries to infer a subcore, and the subcore will then enter something we call attention buffer or cycling events queue, and the subcore usually has will then, for instance, be processed next, and then the process repeats until it at some point might come to a point where the precondition of implication is already satisfied, but there is something like a operation attached to the link. So at this point, it can then invoke a behavior to get the next step, essentially. So to reach a certain subcore. So it's essentially it tries to search in all kind of directions by inference, and some of those directions can then meet with current circumstances, and whenever this is the case, it can invoke an operation in order to reach the next subcore. This is how it's currently handled. So it's a quite simple process, but more tricky, as you mentioned. It would be great if it could do some kind of hierarchical planning, or to be able to handle a hierarchical structure. It's not yet quite clear how to do this the best way. And so far it works especially well if there are just some change from subcores to a certain core the system wants to reach. This works pretty well, but ideally it would be able to handle some cases like traditionally handled by hierarchical planning. But there's still a lot of work to do.
Yeah, I mean, that's, I guess, learning hierarchical plans, if you have enough data presented in the properly staged way, should be possible, right? But, I mean, but that's, thinking about it in a NARS context is interesting though, because all my thinking about causality in the last 10 years has been sort of information theory, which is pretty much probability theory with logarithms, right? And then the connection between information theory and algorithmic information theory. And then in NARS, since it's not probabilistic, the information theory and algorithmic information theory models of causality don't directly pertain, but the basic sort of grounding of causality in action pertains, right? So it's still like a, you know, if me throwing this coffee cup causes it to break, you still have the grounding in this do relation, that this action implies the result. So it's kind of an interesting exercise to think about what aspects of causation can be abstracted and aren't tied to specifics of information and probability. I had not thought about that much. But the hierarchical planning part should be fine, right? Cool.
Especially it seems to be difficult to make sure the system forms the right categories. For instance, because when we plan ahead, for instance, to go to the airport to fly to another country, we don't plan every motor action, right? We only plan in, we say something like at first we have to leave the house, then we take the train to the airport, and so we have quite a high level representation of which actually to be executed only then when we think about step, only then we begin to think about the details.
But do you think that's qualitatively different than learning abstraction hierarchies of concepts in domains other than planning, or is it basically the same problem?
I hope it's the same.
Yeah, right.
Maybe the key about hierarchical planning is just to build a confidence about the planning itself and about the capacity to fill the blanks. And then once you have this confidence, then you can say, okay, well, I plan this, and then I'll figure out, and I'll figure out what's in between, and I know I can figure it out. And then normally you should be able just to to have a formal proof. I mean, a formal proof of an estimate that say, well, yeah, you're gonna solve the goal because you have that confidence how you're gonna be able to.
It just feels to me like when a human is doing a travel plan or something, we come to that with a very rich abstraction hierarchy of relevant concepts already. It's not like we're not usually learning those concepts in the context of forming the plan. We have those concepts in our head already, and so then we naturally use them in forming a plan. I guess in some cases, I mean, if you're learning to play a totally new video game from scratch, then you may be forming the concepts why you plan how to win, and there's some more sort of equally weighted feedback between those two processes. But that seems harder than most of the planning we do in everyday life. It seems like mostly we have the abstraction hierarchy already.
Great, that's a good point.
But maybe it's not true for like a 6-month-old baby, right? I mean, I think it's true. It's true for me now, but I'm mostly operating in environments I've been operating with for decades, right? If you look at a little kid that's planning how to build something with a new set of blocks or something, I guess they're trying to build that tower, and as they try to build that tower, they're learning the properties of the blocks they're building the tower with. And so that, I guess that they're in that preschool setting, you do sort of have that feedback between planning and then concept formation from the objects. And that, I think, of course, that's why we designed that environment to have very simple goals and very easily categorized objects. And it still takes these brains like months or years to solve this coordinated problem of planning and concept formation. But yeah, this sort of ties in. Nil and I and some others in the OpenCog just starting to get back into this sort of toy Minecraft-like domain for learning, because I mean we've been working on all sorts of other stuff, but it seemed like now we're facing some questions where it would be cool to try some really simple domain, just to do some exploratory work. And yeah, building stuff in a Minecraft-like domain that seems to be a case where the plans and the concept formation may be co-learned. Huh? But it's interesting that it's hard to come up with good examples for that in everyday adult life, actually, because I guess, see, as adults we can learn very big, complex hierarchical plans. Little kids tend not to do that. So I mean, seems like when the concept learning and the planning are like co-evolving, you're looking at pretty simple plans, and it's only the really large, well fleshed out hierarchical ontology that lets us come up with the fiendishly complex plans that
yeah, we're coming back to the difference between common sense reasoning and mathematical reasoning, where, well, common sense reasoning, there's no point going beyond a few steps because the uncertainty.
Yeah, but there's other things, like you're looking at like business strategy or planning a military campaign. These are not quite common sense and they're not quite mathematical, but they are they require quite complex planning beyond what a preschool kid can do, right? And then maybe they do use common sense reasoning in the sense of uncertain reasoning, like PLN is doing. But I mean, we also tend to use written aids for these as humans, right? Like they go beyond our working memory in some sense. I mean, planning a complex software project is the same thing. It's not math, but it's not common sense either. More questions from YouTube. Here's a question. Can we build progressive lattice of instantiated causal knowledge upon which to project perceptual understanding of impact, in which over time aspects can be instantiated as extensions? Yes. All right, that's easy. I mean,
how long is the better question?
Yeah. When it will be delivered is another problem.
But yes, we can.
I mean, I think
Conceptually.
that's sort of just what was coming out in the discussion with Patrick, like that lattice, that hierarchy of instantiated causal knowledge is part of your ontology of the world, which is how you can make these high level plans. I mean,
So should we
yeah,
set
the role of scale is interesting to think about here, right? Because I mean, we've seen things like, you know, multi-layer perceptrons for image processing didn't work too well in the 90s. Now they work extremely well. And a lot of this is the scale allowed you to tune and fiddle with the algorithms to get them to work very well by making it so much faster to run experiments. I mean, as well as making it faster to run the trained models. So that the experiment of running like common sense logic engines for causal reasoning on the scale of like what OpenAI is doing with neural nets. I mean, that hasn't been done yet, right? And so it is by doing so, some things that seem to be conceptual problems now may turn out to not be problems at all, and just be problems of inadequate data. Because to build this deep concept hierarchy just requires a large amount of rich information to feed in. I mean, yeah, causation is very sort of impure concept, at least causation as humans understand it conceptually. And I guess we come to it from a whole lot of experience with trying to manipulate physical objects and humans and groups of humans through our childhood. And we haven't yet seen what an AI can do when fed with that kind of data.
I personally
But
think
we
it's
will hopefully in the next few years, right? I mean, now we're kind of poised for it. So.
I think it's more complex than just throwing more hardware at it, though. I think it's like you were talking.
It is
the algorithms with the hardware.
Yeah, but if you take the deep neural net analogy, like the exact multi-layer perceptrons I was teaching in the 90s with recurrent backpropagation, like still don't do very much, right?
Right.
Exactly. On the other hand, having faster computers made it much easier to figure out which variation on that architecture worked well. And like transformer networks, which we're using for our applied work on natural language processing now, and also trying to hybridize with symbolic grammar learning in a paper that Andres Suarez is giving in this conference for unsupervised grammar induction. I mean, these are certainly different than neural nets from 10 years ago, but they're also not that different, right? I mean, all the ingredients were there. It's just no one was smart enough to figure out how to combine them purely with pencil and paper, right? Like you figured out how to combine them by being able to fairly rapidly experiment with variations on the architecture. And I think that cycle hasn't happened with symbolic, like uncertain logic for causal reasoning yet, right? There's been a lot of nice math written down and experiments done on toy problems, and experiments with extremely simplified versions on large data sets. And the more fully fleshed out theories we've never been able to experiment with them in large data sets. So I mean, I certainly, once we can, we're going to figure out many particular things we think are smart now are actually stupid, and make many changes to specific formulas and axioms and so forth. The cool thing is we should soon be in the domain where you can fiddle around with your truth value formulas or the axioms of your logic and see what implications it has for a system doing causal reasoning on like on a realistic body of knowledge, which is by soon I mean within a few years. I don't think we're there quite yet, because we don't have a scalable implementation of any of these. I mean, we don't have an implementation that allows large scale rapid experimentation with the suitably complex versions of these AI tools we're talking about here. We could run pattern mining on a huge distributed atom space if we want to, but we're going to see constraints in how we configure it, so that to get it to work scalably on a huge atom space, you'll have to restrict what sorts of patterns you're looking for and how the search is proceeding. And I think these restrictions will gradually get lifted over the next few years, so we can really let these algorithms operate in more generality on real world data sets. I mean, as an example, letting pattern mining run where it's doing a little inference to check whether a certain sub-atom space matches the pattern. Like right now, that just slows things down so much. You can only do it on small problems. If you want a large problem, you can't be folding the inference through the pattern mining like that.
So maybe some kind of a compilation approach, or just-in-time compilation approach might scale things up. I mean, maybe some kind of a setup where a system which enough these building blocks, logical and probabilistic building blocks, is looking at how things are being executed on a CPU or GPU, and then automatically is trying to create these implementations, very specialized implementations, which might speed up or speed up computation, which is required to get some inference or conclusions, and then create maybe automatically, maybe with some kind of human guidance, the next level, the next layer of the.
You know, I was friends in the late 90s and early aughts with Valentin Turchin, who was sort of the founder of Russian AI in the 60s. He lived in New York then, and he invented super compilation in the 1960s and 70s. So his way to make human level AGI, in essence, it was like take AXE, although he didn't call it that, he had the idea. Take AXE and program specialize it to the human body, and then you're done, right? So, yeah. But there was a problem of scaling up the program specializer, right? So yeah, I think yeah, certainly there has to be the ability for the system to automatically specialize its cognitive operations, for example, inference control heuristics to the specific problems that it's looking at. And I think I mean, that requires a pretty advanced cognitive system, but it has to be there. Like I think, like one, you know, you remember if you studied inorganic then organic chemistry, you have to tweak your inference control mechanism to deal with organic chemistry because the molecules are so big and there's so much there. Or in a preschool context, when kids go from like Duplo blocks, which are big Lego blocks, to the smaller Lego blocks, you know, you have some transfer learning, but you also have some change of the inference control heuristic, like the way they're reasoning about what to build is different with the little blocks because they stick together better. They stick together better, so you can build bigger and more complex things. But that then you get hierarchical plans, which you can't ever get to with the smaller blocks, right? And you then, because you have these hierarchical plans, then you need different inference control heuristics. So I think yeah, you need. I mean, this was one of Nils and my ideas for a while. Pattern mining is like the base case for learning inference control heuristics. So you do a lot of inference. You do pattern mining on the saved inference DAGs. Then using those patterns that you mined, that forms a distribution over which inference paths are good. But that's the base case of the recursion. Then the next case is using inference to infer about which patterns in inference trees are useful in which contexts. But context dependence is the crazy part, right? Because the inference control heuristic for inferring things about similarity between people may be different than the inference control heuristics for inferring about, say, logistical planning or something, right? But then you can explicitly represent the context dependence of an inference control heuristic in the atom space, and then that context dependence is part of the data fed into the inference engine. And the human brain obviously does all this in its own way with a less explicit knowledge representation, right? All right, yeah, we have some lighter weight questions here, or so heavyweight they have to be treated as lightweight. Like one, OpenCog seems to be about intelligence. Is there any work on sentience? Is that necessary or sufficient for the other? So, I mean, intelligence, we have some formal definitions of, which you may or may not accept, but at least they're there. Sentience is a lot vaguer, right? So, I mean, if you're thinking about sort of practical, reflective consciousness like humans have, where we have a working memory and a knowledge of ourself and others and so forth. I mean, this I think would come from using a system like the one we're building in OpenCog to control, an autonomous agent moving around in a physical environment and communicating with other similar agents in a shared environment. So I think the structures of self and others and the illusions of free will and identity and all these things that make our inner lives what they are, in a structural and dynamic sense, I think those would come out of putting this kind of learning algorithm to do the kind of task that humans do. I mean, then you have the whole qualia problem of like, would this thing feel like people do, which is a whole other philosophy problem that I don't want to try to answer here, although I've written a lot about it in the past. I mean, I tend to be panpsychist and think everything in the universe is conscious. And so if the structures and dynamics in this digital system are vaguely like those in a human, then maybe its subjective experience will be vaguely like those in a human. But that's a whole other deep philosophical story. And I guess most of our thinking in OpenCog project is you can build something that appears to think like a human or even smarter than a human without necessarily fully solving that philosophy problem of the nature of experience, which we haven't solved in the human domain either. All right, I seem to have accidentally taken over this Q&A session due to having a bigger mouth than everybody else. But maybe someone else has something to say now.
Who will dare? Let's see.
Well, there was another question. Could we use a biological approach to build increasingly complex capabilities of organisms by using causal relationships between concepts? I don't know what a biological approach means in this context. I think both in like evolutionary algorithms and in algorithmic chemistry, as I mentioned, you're certainly being inspired by biology. And for the algorithmic chemistry concept I mentioned, there was a blog post I had 4 or 5 years ago, which I called cogistry, very ugly word, which I hope doesn't catch on. But anyways, cogistry, like cognitive chemistry. I tried to explain this soup of intercreating codelets with inference and probabilistic reasoning and pattern mining to accelerate its evolution. But I mean, these are very loosely biologically inspired. And I guess if you really get deep into biology and artificial life, it's cool, but it brings you in a whole different direction, right? Because I mean, the reason biology is as generative as it is, generating so many different cool things that actually work, comes down to chemistry. And then the reason chemistry works is physics. And then it's like either you have the periodic table of elements and molecular orbitals and all that, or you try to understand what are the principles that make the periodic table work as nicely as it does, which is very, very cool. However, and that may be a way to make AGI, but that's a whole other direction to take, right? So I think when you think deeply about AGI, eventually you realize like human-like minds are a very tiny corner of the subspace of all possible generally intelligent minds. And there's probably a host of different ways to even implement human-like minds, let alone other types of minds. So the challenge we have is to find a way that will work tractably, right? And once you have that, then that either by its own thinking or as a tool to help your research, that first mind can help you explore all the other avenues, which is it's probably a good note to end this long, rambling, and hopefully entertaining Q&A session on. So yeah, thanks everyone for attending the tutorial and the follow-on wide-ranging discussion. And yeah, thanks to Nil and Matt and everyone from the OpenCog side for leading things. So Ibi, do you want to give an overview of what's up for tomorrow?
Yep, sure. Yeah, again, thank you, everybody. So for tomorrow, we have some more tutorials and workshops lined up in room 1, which is on our YouTube channel. You can find the on logic and probability synthesis and AGI tutorial, and applied neural symbolic integration using OpenCog. And in room 2, also on our YouTube channel, you can find the NARS workshops. There are a whole list of things that they will be talking about and sharing with you. So it's going to be really, really interesting. Yeah, so stay tuned, and we will see you tomorrow.
Thanks, everyone.
Thank you.
Bye.